History of Phobos. Phobos was discovered by astronomer Asaph Hall on August 18, 1877 at the United States Naval Observatory in Washington, D.C. at about 9:14 Greenwich Mean Time. Contemporary sources using the pre-1925 astronomical convention that began the day at noon give the time of discovery as August 17, 1606 Washington Mean Time, meaning August 18th, 406 in the modern convention. Hall had discovered Deimos, Mars's other moon, a few days earlier on August 12, 1877 at about 7:48 UTC. The names, originally spelled Phobos and Deimos respectively, were suggested by Henry Madden, 1838 to 1901, science master at Eton College, based on Greek mythology, in which Phobos is a companion to the god Eris. Speculation about the existence of the moons of Mars had begun when the moons of Jupiter were discovered, when Galileo Galilei, as a hidden report about him having observed two bumps on the sides of Saturn, later discovered to be its rings. Hall recorded his discovery of Phobos in his notebook as follows: I repeated the examination in the early part of the night of 11th August 1877, and again found nothing. But trying again some hours later, I found a faint object on the following side and a little north of the planet. I'd barely time to secure an observation of its position when fog from the river stopped the work. This was at 2:30 o'clock on the night of the 11th. Cloudy weather intervened for several days. On 15 August, the weather looking more promising, I slept at the observatory. The sky cleared off with a thunderstorm at 11 o'clock, and the search was resumed. The atmosphere, however, was in a very bad condition, and Mars was so blazing and unsteady that nothing could be seen of the object, which we now know was at that time so near the planet as to be invisible. On 16 August, the object was found again on the following side of the planet, and the observations of that night showed that it was moving with the planet, and if a satellite was near one of its elongations. Until this time, I had said nothing to anyone at the observatory of my search for a satellite of Mars, but on leaving the observatory after these observations of the 16th, at about 3 o'clock in the morning, I told my assistant George Anderson, to whom I had shown the object, that I thought I had discovered a satellite of Mars. I told him also to keep quiet, as I did not wish anything said until the matter was beyond doubt. He said nothing, but the thing was too good to keep, and I let it out myself. On 17 August, between 1 and 2 o'clock, while I was reducing my observations, Professor Newcomb came into my room to eat his lunch, and I showed him my measures of the faint object near Mars, which proved that it was moving with the planet. On 17 August, while waiting and watching for the outer moon, the inner one was discovered. The observations of the 17th and 18th put beyond doubt the character of these objects, and the discovery was publicly announced by Admiral Rogers. Orbits and rotations. The orbital motion of Phobos has been intensively studied, making it the best studied natural satellite in the solar system in terms of orbits completed. Its close orbit around Mars produces some unusual effects. With an altitude of 5,989 kilometers, or 3,721 miles, Phobos orbits Mars below the synchronous orbit radius, meaning that it moves around Mars faster than Mars itself rotates. Therefore, from the point of view of an observer on the surface of Mars, it rises in the west, moves comparatively rapidly across the sky in 4 hours, 15 minutes or less, and sets in the east approximately twice each Martian day, every 11 hours and 6 minutes. Because it is close to the surface and in an equatorial orbit, it cannot be seen above the horizon from latitudes greater than 70.4 degrees. Its orbit is so low that its angular diameter, as seen by an observer on Mars, varies visibly with the position in the sky. Seen at the horizon, Phobos is about 0.14 degrees wide. At zenith, it is 0.20 degrees, 1/3 as wide as the full moon is seen from Earth. By comparison, the Sun has an apparent size of about 0.35 degrees in the Martian sky. Phobos's phases, in as much as they can be observed from Mars, take 0.3191 days. Phobos's synodic period to run their course, a mere 13 seconds longer than Phobos's sidereal period. As seen from Phobos, Mars would appear 6,400 times larger and 2,500 times brighter than the full moon appears from Earth, taking up a quarter of the width of a celestial hemisphere. An observer situated on the Martian surface, in a position to observe Phobos, would see regular transits of Phobos across the Sun. Several of these transits have been photographed by the Mars rover Opportunity. During the transits, Phobos' shadow is cast on the surface of Mars, an event which has been photographed by several spacecraft. Phobos is not large enough to cover the Sun's disk and so cannot cause a total eclipse. Surface. Phobos and Deimos appear to be composed of C-type rock, similar to blackish carbonaceous chondrite asteroids. Observations by Mars Global Surveyor indicate that the surface of this small body has been pounded into powder by eons of meteoroid impacts, some of which started landslides that left dark trails marking the steep slopes of giant craters. Measurements of the day and night sides of Phobos show such extreme temperature variations that the sunlit side of the moon rivals a pleasant winter day in Chicago, while only a few kilometers away on the dark side of the moon, the climate is more harsh than a night in Antarctica. High temperatures for Phobos were measured at 25 degrees Fahrenheit, -4 degrees Celsius, and lows at -100 degrees Fahrenheit, -112 degrees Celsius. This intense heat loss is likely a result of the fine dust on Phobos' surface, which is unable to retain heat. Controversial origin. The origin of the Martian moons is still controversial, which is interesting given how long we've been studying them. Phobos and Deimos both have much in common in regards to their composition and even their shape and size in certain areas. Based on their similarity, one hypothesis is that both moons may be captured main belt asteroids. Both moons have very circular orbits which lie almost exactly in Mars' equatorial plane, and hence a capture origin requires a mechanism for circulating the initially high eccentric orbit and adjusting its inclination to the equatorial plane, most probably by a combination of atmospheric drag and tidal forces. Although it is not clear that sufficient time is available for this to occur for Deimos, capture also requires dissipation of energy. The current Martian atmosphere is too thin to capture a Phobos-sized object by atmospheric braking. Jeffrey A. Landis has pointed out that the capture could have occurred if the original body was a binary asteroid that separated under tidal forces. Phobos could be a second-generation solar system object that coalesced in orbit after Mars formed, rather than forming concurrently out of the same birth cloud as Mars. Another hypothesis is that Mars was once surrounded by many Phobos and Deimos-sized bodies, perhaps ejected into orbit around it by a collision with a large planetesimal. The high porosity of the interior of Phobos is inconsistent with an asteroidal origin. Observations of Phobos in the thermal infrared suggest a composition containing mainly phyllosilicates, which are well known from the surface of Mars. The spectra are distinct from those of all classes of chondrite meteorites, again pointing away from an asteroidal origin. Both sets of findings support an origin of Phobos from material ejected by an impact on Mars that reaccreted in Martian orbit, similar to the prevailing theory for the origin of Earth's moon. The irony here is that it's hard to tell which of these theories is true, especially since we're still evaluating the origins of Mars itself. Only through various tests on both the planet and the moons can we likely find the truth of what is going on. Could Phobos be hollow? If it's not clear by now, Phobos is a very unique moon compared to many of the others within our solar system, but one man has noted that there may just be a unique way of explaining it all. Mainly, this person believes that Phobos could be hollow. Around 1958, Russian astrophysicist Iosif Samuelovich Klovsky, studying the secular acceleration of Phobos' orbital motion, suggested a thin sheet metal structure for Phobos, a suggestion which led to speculations that Phobos was of artificial origin. Klovsky based his analysis on estimates of the upper Martian atmosphere density and deduced that for the weak braking effect to be able to account for the secular acceleration, Phobos had to be very light. One calculation yielded a hollow iron sphere 16 kilometers, 9.9 miles across, but less than 6 centimeters thick. In a February 1960 letter to the journal Astronautics, Fred Singer, then science advisor to U.S. President Dwight D. Eisenhower, said of Klovsky's theory, If the satellite is indeed spiraling inward as deduced from astronomical observation, then there is little alternative to the hypothesis that it is hollow and therefore Martian-made. The big if lies in the astronomical observations. They may well be in error, since they are based on several independent sets of measurements taken decades apart by different observers with different measurements. Systematic errors may have influenced them. These errors were indeed found, and later observations and investigations revealed that Phobos is a kind of rubble pile moon. In addition, images obtained by the Viking probes in the 1970s clearly showed a natural object, not an artificial one. Nevertheless, mapping by the Mars Express probe and subsequent volume calculations do suggest the presence of voids and indicate that it is not a solid chunk of rock, but a porous body. So while it was a curious theory, and one that would have rewritten history, it was not one that was proven to be true by any metric. Could Phobos be destroyed via natural patterns? Tidal deceleration is gradually decreasing the orbital radius of Phobos by 2 meters every 100 years. Scientists estimate that Phobos will be destroyed in approximately 30 to 50 million years, with one study's estimate being about 43 million years. Phobos' grooves were long thought to be fractures caused by the impact that formed the Stickney crater. Other modeling suggested since the 1970s support the idea that the grooves are more like stretch marks that occur when Phobos gets deformed by tidal forces. But in 2015, when the tidal forces were calculated and used in a new model, the stresses were too weak to fracture a solid moon of that size, unless Phobos is a rubble pile surrounded by a layer of powdery regolith about 100 meters or 330 feet thick. Stress fractures calculated for this model line up with the grooves on Phobos. The model is supported with the discovery that some of the grooves are younger than others, implying that the process that produces the grooves is ongoing. Given Phobos' irregular shape and assuming that it is a pile of rubble, specifically a more Coulomb body, it will eventually break up when it reaches approximately 2.1 Mars radii. When Phobos is eventually torn apart by tidal forces, a fraction of the debris will likely form a planetary ring around Mars, which may last from 1 million to 100 million years. A very interesting end for a very interesting moon. Colony on Phobos? As you all likely know, both NASA and SpaceX are preparing themselves for a mission of grand importance. They're going to try and colonize Mars. This mission will take many years to fully complete, and launch for the first part will be in the next few years. But many are already planning for what is to come after we truly make contact on Mars. Mainly once the main colony is set up, we'll immediately start expanding. Now the initial thought is to go to another planet to colonize, or a moon of a planet beyond Mars. But many are thinking that Mars could be a perfect launch point for a set of colonies. Mainly have a main one on Mars to start, and then have waypoint stations on Phobos and Deimos. But why do that? Because it would allow for easier transition both in and out of Mars's atmosphere, which is thin but still there, and its gravity pull. There are some who even speculate that a certain kind of perpetual motion machine can be put on the moons to help launch ships into the asteroid belt area that separates Mars and Jupiter, and thus make it easier to get into the back half of the solar system. Plus, having bases on the moons could allow for travel between Earth and Mars and beyond, as well as potentially setting up mining stations for going into the asteroid belt and seeking out materials there. Deimos, Mars's moon. Orbits and rotations. Deimos's orbit is nearly circular and is close to Mars's equatorial plane. Deimos is possibly an asteroid that was perturbed by Jupiter into an orbit that allowed it to be captured by Mars, though this hypothesis is still controversial and disputed. Both Deimos and Phobos have circular orbits which lie almost exactly in Mars's equatorial plane, and hence a capture origin requires a mechanism for circulating the initially high eccentric orbit and adjusting its inclination into the equatorial plane, most likely by a combination of atmospheric drag and tidal forces. It is not clear that sufficient time was available for this to have occurred for Deimos. As seen from Mars, Deimos would have an angular diameter of no more than 2.5 minutes. 60 minutes make 1 degree. 1/12 of the width of the moon is seen from Earth, and would therefore appear almost star-like to the naked eye. At its brightest, full moon, it would be about as bright as Venus is from Earth. At the first or third quarter phase, it would be about as bright as Vega. With a small telescope, a Martian observer could see Deimos's phases, which take 1.2648 days, Deimos's synodic period, to run their course. Unlike Phobos, which orbits so fast that it rises in the west and sets in the east, Deimos rises in the east and sets in the west. Because Deimos's orbit is relatively close to Mars and has only a very small inclination to Mars's equator, it cannot be seen from Martian latitudes greater than 82.7 degrees. Deimos's orbit is slowly getting larger because it is far enough away from Mars and because of tidal acceleration. It is expected to eventually escape Mars's gravity, which is in contrast to Phobos, who is having its orbit degraded every 100 years, and is expected to be destroyed by Mars eventually and then become its ring. Size and structure. Deimos is the smaller of Mars's two moons, being only 9 by 7 by 6.8 miles in size, 15 by 12 by 11 kilometers. Like Phobos, Deimos is a small and lumpy, heavily cratered object. Its craters are generally smaller than 1.6 miles or 2.5 kilometers in diameter. However, it lacks the grooves and ridges seen on Phobos. Typically, when a meteorite hits a surface material is thrown up and out of the resulting crater. The material usually falls back to the surface surrounding the crater. However, these ejected deposits are not seen on Deimos, perhaps because the moon's gravity is so low that the ejecta escape to space. Material does not appear to have moved down slopes. Deimos also has a thick regolith, perhaps as deep as 328 feet or 100 meters, formed as meteorites pulverize the surface. Deimos is a dark body that appears to be composed of C-type surface materials, similar to that of asteroids found in the outer asteroid belt. Exploration. Not surprisingly, the exploration history of Deimos is similar to those of Mars and Phobos. Deimos has been photographed in close-up by several spacecraft, whose primary mission has been to photograph Mars. No landings on Deimos have been made. In 1997 and 1998, the proposed Aladdin mission was selected as a finalist in the NASA Discovery program. The plan was to visit both Phobos and Deimos and launch projectiles at the satellites. The probe would collect the ejecta as it performed a slow flyby, around 1 kilometer per second. These samples would be returned to Earth for study 3 years later. The principal investigator was Carl M. Peters of Brown University. The total mission cost, including launch vehicle and operations, was $247.7 million. Ultimately, the mission chosen to fly was Messenger, a probe to the planet Mercury. In 2008, NASA Glenn Research Center began studying a Phobos and Deimos sample return mission that would use solar electric propulsion. The study gave rise to the Hall mission concept, a New Frontiers-class mission currently under further study. Also, the sample return mission called Gulliver has been conceptualized and dedicated to Deimos, in which 1 kilogram, 2.2 pounds, of material from Deimos would be returned to Earth. Another concept of sample return mission from Phobos and Deimos is OSIRIS-REx-2, which would use heritage from the first OSIRIS-REx. Human exploration of Deimos could serve as a catalyst for the human exploration of Mars. Recently, it was proposed that the sands of Deimos or Phobos could serve as a valuable material for aerobraking in the colonization of Mars. Because the small Delta V budget of Phobos, a small amount of chemical fuel brought from Earth could be transformed in a very large amount of sand lifted from the surface of Phobos, from a permanent outpost to a transfer orbit. This sand could be released in front of the spacecraft during the descent maneuver, and then resulting in a desensification of the atmosphere just in front of the spacecraft. Solar transits. Deimos regularly passes in front of the Sun as seen from Mars. It is too small to cause a total eclipse, appearing only as a small black dot moving across the Sun. Its angular diameter is only about 2.5 times the angular diameter of Venus during a transit of Venus from Earth. Its fellow moon, Phobos, also has a similar kind of solar transit because it is too small that it can't block out the Sun. However, it still creates quite the interesting image. On March 4, 2004, a transit of Deimos was photographed by Mars rover Opportunity, and on March 13, 2004, a transit was photographed by Mars rover Spirit. Controversial origins. The origin of the Martian moons is still controversial, which is interesting given how long we've been studying them. Phobos and Deimos both have much in common in regards to their composition and even their shape and size in certain areas. Based on their similarity, one hypothesis is that both moons may be captured main belt asteroids. Both moons have very circular orbits which lie almost exactly in Mars's equatorial plane, and hence a capture origin requires a mechanism for circularizing the initial highly eccentric orbit and adjusting its inclination to the equatorial plane, most probably by a combination of atmospheric drag and tidal forces, although it is not clear that sufficient time is available for this to occur for Deimos. Capture also requires dissipation of energy. The current Martian atmosphere is too thin to capture a Phobos-sized object by atmospheric braking. Jeffrey A. Landis has pointed out that the capture could have occurred if the original body was a binary asteroid that separated under tidal forces. Another hypothesis is that Mars was once surrounded by many Phobos and Deimos-sized bodies, perhaps ejected into orbit around it by a collision with a large planetesimal. The impact on Mars that Rhea created in Martian orbit would be similar to the prevailing theory for the origin of Earth's moon, in which many people believe that a large object smashed into the Earth and the remnants of that impact were caught in the gravity of the Earth and eventually formed into the moon. The irony here is that it's hard to tell which of these theories is true, especially since we're still evaluating the origins of Mars itself. Only through various tests on both planet and the moons can we likely find the truth of what is going on. Odd shape. Go ahead and picture in your mind a moon. More than likely you went and pictured the moon that is orbiting the Earth right now, which is fair. When you think of a moon, you no doubt think of a perfectly spherical object, perhaps one that has a lot of craters like the Earth's moon. But when you look at Deimos as well as its partner Phobos, you'll notice that these moons aren't regular shaped moons. In fact, if you look at Deimos especially, you'll see various dips in its contour that makes it feel more like an asteroid than a regular moon, which again backs up the origin theories that were stated. This is curious for all sorts of reasons, not the least of which is that you could argue that Deimos is one of the oddest moons in the solar system simply because of its shape. Colony material? While the world today doesn't seem like a very hopeful place, there are those who are striving for certain goals in the current decade that can elevate humanity as a whole. And the biggest of those goals is starting the Mars colony. Whether it's by SpaceX or NASA, man is likely going to set foot on the moon this decade. But what happens after that colony is started up? Well, many have asked that question, and many feel that it is very likely that either Phobos or Deimos could be tapped as special waypoint stations or mini colonies for Mars. The applications of these moons could be diversified based on the needs of the main colony, or the desire to further explore into the outer reaches of the solar system. The intent here in many people's minds is to not burden the main Mars colony too much. By putting colonies on the moons, it could act as a buffer to bring in supplies, or allow for easier launches into space, as they'd be truly launching off the moon instead of shooting right into space from Mars. There are a lot of ways this could work. It would just be a matter of intent, time, money, and the ability to build it on the irregular moons. Io. One hell of a moon. Volcanoes are a unique feature of our Earth. Our Earth is relatively new as compared to other solid worlds in our solar system. Some worlds have a few volcanic activities and some worlds lack any volcanic activity. But there is one strange place in our solar system which outclasses everything else in terms of volcanic activity. Galileo discovered 4 massive moons around our largest planet, Jupiter, using a telescope in 1610. Callisto was the farthest out, followed inward by Ganymede, Europa, and lastly, the closest world, Io. While Callisto and Ganymede are enormous and extensively cratered, and Europa appears to be covered in ice, when we take a good close look at Io, it appears to be vastly different from the other worlds. What's so special about Io that makes it stand out in our solar system? While the Earth's crust is the smallest of its layers, it is neither homogeneous nor distinctive. The Earth's crust is thinnest and simplest to penetrate, where the deeper mantle is packed thickest beneath it. In contrast, if the mantle does not begin until it reaches its greatest subterranean depths, the crust accumulates the most. The crust-mantle border is where many events and interactions, including plate tectonics, lead the rocks beneath the Earth's surface to melt. Magma chambers form as a result of this. Because our planet's surface area-to-mass ratio is minimal, as it is for all huge rocky worlds, that energy has a difficult time escaping, building up, then releasing irregularly in catastrophic events such as volcanoes and earthquakes. You're probably familiar with ice melting, and you've probably noticed that ice floats over water because it's less dense in its solid phase than it is in its liquid phase. Water is a fairly uncommon element in this regard, accounting for anything from icebergs in the ocean to ice cubes in your summer drinks. The liquid phase of most materials, including rocks, is less dense than the solid phase, and this means that when magma forms beneath the surface, it both expands, shattering and displacing the rocks on either side, and strives to rise due to its reduced density and buoyancy. When enough magma creates enough pressure, a volcanic eruption occurs, which occurs numerous times every year at various locations around the Earth's surface. However, this is not the case on most rocky planets. In terms of solid worlds, the Earth's crust is rather young. Compare the Earth's surface to that of Mercury or the Moon, where craters have existed for billions of years, untouched and unpolluted by volcanic activity. While the Earth is rife with volcanic eruptions, magma vents, and consistent eruptions, these small, geologically inactive, at least relatively inactive, worlds haven't had a good resurfacing since the solar system's inception. Volcanoes do occur on worlds you might not expect, such as Jupiter's tiny moon Io. Io appears to be an odd choice for volcanoes, with only 1.5% of Earth's mass, but having more than a quarter of the Earth's diameter, as 4.5 billion years is more than enough time for it to have cooled and become stable. However, Io is far from stable, since a slew of volcanic eruptions were anticipated before we even had a good look at it. When the Voyager 1 spacecraft visited Io, it discovered hundreds of volcanic calderas, including genuine eruptions with plumes 300 kilometers high. Following that, observations from Voyager 2, Galileo, and a slew of telescopes revealed that these eruptions alter fast on Io's surface. While Callisto and Ganymede are enormous and extensively cratered, and Europa appears to be covered in ice, when we take a good close look at Io, it appears to be vastly different from the other worlds. To be sure, it's covered with rock and has a pockmarked face, a little like an adolescent who can't stop scratching. However, there is one feature of Io that distinguishes it from the other stony worlds we've discovered. There are no craters. As we've learned, there's a good reason for this, and if you thought Earth's tides were bad, you haven't seen anything until you've seen Io's. But have you noticed Io's two bright spots? Those are active volcanoes, which are currently erupting. If you're used to seeing volcanoes on Earth, you could assume this is a once-in-a-lifetime occurrence that we just happened to witness. After all, if they can light up the world's surface like this, these must be rather stunning eruptions, and there are two of them going on at the same time. However, a deeper examination, or rather persistent examinations of Io, reveals that these eruptions are extremely prevalent. Io's surface is the most recent in the solar system. Why don't there appear to be any craters on its surface? On timescales of thousands to tens of thousands of years, these eruptions cover the entire globe in a fresh coat of lava, which hardens into rock. What is causing this? The answer is straightforward. Jupiter, which works as a cosmic Zamboni on Io, creating resurfacing and surface lava as if it had nothing else to do in the universe. All of this energy is because of the combined tidal forces of Jupiter and the outer Jovian moons. On Earth, gravity from the Sun and Moon causes ocean tides to rise and fall by 1 to 2 meters on average, which is far too little to create significant heating. Despite the fact that Io lacks oceans, the tidal forces acting on it cause the world to stretch and bend by an astounding 100 meters at a time. This not only causes cracking and fissures, but also heats up the planet's interior, similar to how rapidly bending a piece of metal back and forth causes it to heat up internally. When a path to the surface opens up, that internal heat escapes through quiescent lava flows and catastrophic volcanic eruptions. The hottest points on Io's surface reach 1200 degrees Celsius or 2000 degrees Fahrenheit, in comparison to the average surface temperature of 110 Kelvin, minus 163 degrees Celsius, or minus 261 degrees Fahrenheit. Io has the most dramatic temperature changes across locations outside of the Sun. The combined effects of the Moon and Sun on Earth generate minor tides, raising and lowering the oceans by 1 meter at a time and causing the crust to swell and shrink by millimeters or centimeters with each rotation. But on Io, the tidal forces caused by Jupiter are enormous, 10,000 times stronger than what we experience here on Earth. And this is significant enough to rend the surface of Io apart with almost every orbit of the Moon around its shepherding planet. While our tides cause the oceans to rise and fall, Jupiter's tides create magma just beneath Io's surface, then rip that surface apart, allowing it to rise to the crust in a constant state of eruption. If our Moon were 20 times closer to Earth than it is now, the tidal forces on our planet would have the same effect, rendering our planet virtually uninhabitable, as Io does. Fortunately, the Moon is at a safe distance, and any resurfacing is caused by Earth's own physics rather than the tidal influence of a cataclysmic outsider. But as Jupiter wreaks havoc on Io, Europa lies just far enough out in what is possibly the sweetest place of all. Io becomes deformed, heats up, and explodes simply by orbiting where it does, making it the most volcanically active world in the entire solar system. Other moons orbiting gas giants have stunning eruptions as well. For example, Enceladus orbiting Saturn. But no world surface is as molded by volcanic activity as Jupiter's innermost moon, Io. While Jupiter's surface is covered in ice, the heat generated by its tides should be sufficient to support undersea magma vents, a heat source, and a liquid ocean deep beneath the ice. NASA recently announced a mission to Europa to investigate whether the Moon contains the ingredients required for chemical-based life. A tantalizing possibility. While this Zamboni-like effect is disastrous for Io, the most active and resurfaced world in the solar system, a light version of it may have been exactly what its neighboring world required to give rise to the most fragile and spectacular combination of atoms we've ever discovered. A self-reproducing, information-encoding, sustaining set of reactions we call life. It's remarkable what a little, or a lot, in a different sense, of push and pull can do. Europa, Jupiter's veiny eyeball moon. The discovery of Europa. Europa is just one of many moons around Jupiter, and each one has a history that is all their own, including their discovery by a certain legendary astronomer. Europa, along with Jupiter's 3 other large moons, Io, Ganymede, and Callisto, was discovered by Galileo Galilei on January 8, 1610, and possibly independently by Simon Marius, though Galileo himself has called this a false claim, and because he was the first to truly document it, he was given the credit. Ironically, at first, Galileo couldn't separate Europa and Io in the sky because of the light that they were giving off. Thus, he had to wait another day and then found out that they were indeed 2 separate moons. Europa is named after Europa, daughter of the king of Tyre, a Phoenician noblewoman in Greek mythology. Like all the Galilean satellites, Europa is named after a lover of Zeus, the Greek counterpart of Jupiter. Europa was courted by Zeus and became the queen of Crete. The naming scheme was suggested by Simon Marius, who attributed the proposal to Johannes Kepler. The names fell out of favor for a considerable time and were not revived in general use until the mid-20th century. In much of the earlier astronomical literature, Europa is simply referred to by its Roman numeral designation as Jupiter 2, a system also introduced by Galileo, or as the second satellite of Jupiter. In 1892, the discovery of Amalthea, whose orbit lay closer to Jupiter than those of the Galilean moons, pushed Europa to the 3rd position. The Voyager probes discovered 3 more inner satellites in 1979, so Europa is now counted as Jupiter's 6th satellite, though it is still referred to as Jupiter 2. And think about it, all of that struggle just to find and then name a singular moon. Size and relation to Jupiter. With an equatorial diameter of 1,940 miles or 3,100 kilometers, Europa is about 90% the size of Earth's moon. So if we replaced our moon with Europa, it would appear roughly the same size in the sky as our moon does, but brighter. Much, much brighter. Europa's surface is made of water ice, and so it reflects 5.5 times the sunlight than our moon does. Europa orbits Jupiter at about 417,000 miles or 671,000 kilometers from the planet, which itself orbits the Sun at a distance of roughly 500 million miles or 780 million kilometers, or 5.2 astronomical units, AU. 1 AU is the distance from Earth to the Sun. Light from the Sun takes about 45 minutes to reach Europa. Because of the distance, sunlight is about 25 times fainter at Jupiter and Europa than at Earth, which is important to note for several reasons, not the least of which is because when it comes to sunlight, you need it to be strong to harness its energy, which is why solar power is feasible on Earth. On Jupiter, or in this Europa, that wouldn't be as feasible because the fainter wouldn't generate as much power. Despite this, though, as noted, the reflective surface does harness the light that does not come around and makes the surface much brighter, which has helped in part to the various probes and satellites that have tried to study it over the years. Orbits and rotations. Europa orbits Jupiter every 3.5 days and is locked by gravity to Jupiter, so the same hemisphere of the moon always faces the planet. Jupiter takes about 4,333 Earth days, or about 12 Earth years, to orbit the Sun, a Jovian year. Jupiter's equator and the orbital plane of its moons are tilted with respect to Jupiter's orbital path around the Sun by only 3 degrees. Earth is tilted 23.5 degrees. This means Jupiter spins nearly upright, so that the planet, as well as Europa and Jupiter's other dozens of moons, do not have seasons as extreme as other planets do. Jupiter's moons Io, Europa, and Ganymede are in what is called a resonance. Every time Ganymede orbits Jupiter once, Europa orbits twice, and Io orbits 4 times. Over time, the orbits of most large satellites or planets tend to become circular. But in the case of these 3 satellites, the resonance produces a forced eccentricity since the satellites line up with each other at the same points in their orbits over and over, giving each other a small gravitational tug that keeps their orbits from becoming circular. Because Europa's orbit is elliptical, slightly stretched out from circular, its distance from Jupiter varies, and the moon's near side feels Jupiter's gravity more strongly than its far side. The magnitude of this difference changes as Europa orbits, creating tides that stretch and relax the moon's surface. Flexing from the tides likely creates the moon's surface fractures. If Europa's ocean exists, the tidal heating could also lead to volcanic or hydrothermal activity on the seafloor, supplying nutrients that could make the ocean suitable for living things. Surface. Europa's water ice surface is crisscrossed by long linear fractures. Based on the small number of observable craters, the surface of this moon appears to be no more than 40 to 90 million years old, which is youthful in geologic terms. The surface of Callisto, another of Jupiter's moons, is estimated to be a few billion years old. Along Europa's many fractures and in splotchy patterns across its surface is a reddish-brown material, whose composition is not known for certain, but likely contains salts and sulfur compounds that have been mixed with the water ice and modified by radiation. This surface composition may hold clues to the moon's potential as a habitable world. NASA's Galileo spacecraft explored the Jupiter system from 1995 to 2003 and made numerous flybys of Europa. Galileo revealed strange pits and domes that suggest Europa's ice layer could be slowly churning or convecting. Cooler, denser ice sinks while warmer, less dense ice rises due to heat from below. Long linear fractures are often only 1 to 2 kilometers wide, but can extend for thousands of kilometers across Europa's surface. Some of these fractures have built up into ridges hundreds of meters tall, while others appear to have pulled apart into wide bands of multiple parallel fractures. Galileo also found regions called chaos terrain, where broken, blocky landscapes were covered in mysterious reddish material. In 2011, scientists studying Galileo data proposed that chaos terrains could be places where the surface collapsed above lens-shaped lakes embedded within the ice. Atmosphere. Europa has only a tenuous atmosphere of oxygen, but in 2013, NASA announced that researchers using the Hubble Space Telescope found evidence that Europa might be actively venting water into space. This would mean that the moon is geologically active in the present day. If confirmed by follow-up observations, the plumes of water could be studied by future spacecraft, similar to how the Cassini sampled the plume of Saturn's moon Enceladus. Granted, we haven't seen the plumes in any way, not even with still imagery, but the water vapor had to get there somehow, right? Clearly the ice on the surface didn't melt and somehow rise up. It's too far from the sun to do that. So how else could it have gotten up there? Water plumes, that's how. This discovery is changing everything we've ever thought about the moon, as well as determining why it could be a big step towards not just finding life on other places, but how this place could be a potential colonization spot. Essential chemical elements, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, and sources of energy, 2 of 3 requirements for life, are found all over the solar system. But the third, liquid water, is somewhat hard to find beyond Earth, said Lucas Paganini, a NASA planetary scientist who led the water detection investigation. While scientists have not yet detected liquid water directly, we found the next best thing: water in vapor form. Pop culture. Europa has been featured in short stories, comics, and novels, with perhaps the best known being the Arthur C. Clarke novel, 2010 Odyssey 2, which was also adapted for film. More recently, Europa was the setting for the 2013 film Europa Report, and it was featured in an episode of the animated television show Futurama. The moon has also been the setting or subject of several video games, including Call of Duty Infinite Warfare and Galaga Destination Earth. So clearly this moon has had a lot of popularity, or else it wouldn't be used this much. And as we continue to try and expand across the universe, there's little doubt that Europa will be home to more pop culture references as people learn even more about it. Exploration past and future. Jupiter and its moons have been a focal point for astronomers for literal centuries. Ever since Galileo found some of the moons, many have tried to get closer to them and explore their many facets. Exploration of Europa in the modern age began with the Jupiter flybys of Pioneer 10 and 11 in 1973 and 1974 respectively. The first close-up photos were of low resolution compared to later missions. The 2 Voyager probes traveled through the Jovian system in 1979, providing more detailed images of Europa's icy surface. The images caused many scientists to speculate about the possibility of a liquid ocean underneath. Starting in 1995, the Galileo space probe orbited Jupiter for 8 years, until 2013, and provided the most detailed examination of the Galilean moons to date. It included the Galileo Europa mission and Galileo Millennium mission, with numerous close flybys of Europa. In 2007, New Horizons imaged Europa as it flew by the Jovian system while on its way to Pluto. Further missions are planned to explore the moons and the back half of the solar system as a whole. Life on Europa? Europa is one of the few places in the solar system, aside from Earth, for which there is very strong evidence suggesting a liquid water ocean is present today and is in contact with rock. This is important because life as we know it requires 3 key basic ingredients: liquid water, an energy source, and organic compounds to use as the building blocks for biological processes. Europa could have all 3 of these ingredients, and its ocean may have existed for the whole age of the solar system, long enough for life to begin and evolve there. But while Europa may turn out to have the necessary ingredients for life, it may still be lifeless. After all, having all the ingredients to make a pie is not the same as having a pie. What's more, given all the exploration that has been done near Europa, you would expect us to have gotten some clues that life of any kind is there, and yet that hasn't been the case as of yet. If we eventually find some form of life at Europa, or Mars, or Enceladus for that matter, it may look like microbes or maybe something more complex. If it can be demonstrated that life formed independently in 2 places around the same star, it would then be reasonable to suspect that life springs up in the universe fairly easily once the necessary ingredients are present, and that life might be found throughout our galaxy and the universe. But even the prospect of it potentially having life is enough to get some people going and wanting to search for more clues and evidence one way or another, if for no other reason than to help ourselves in regards to building our own life on the moon. Colonization? That is the question, isn't it? With everything we know about it, do we think we can colonize the moon of Jupiter? Technically speaking, yes it does. The idea of colonizing a moon is not far-fetched. The problem has always been whether the moon makes sense for us to live on. For example, we can't really live on our moon despite it being so close because it doesn't have an atmosphere, or at least not in the sense that many picture. It doesn't have enough ice or any kind of water that we can use, and it doesn't have a natural energy source that we know of. That can work in our favor to make things easier to live on it. We can explore it fine as we've shown, but barring advances in technology, it's not a feasible and logical place to live. While Europa is much farther away, it has things we can use to make colonization more plausible. For example, as noted earlier, the atmosphere may be thin, which isn't ideal, but it does have a lot of oxygen, which means we could use that in our colonies to survive. We wouldn't be able to live on the surface without protection, but the air that we could breathe would theoretically be much easier to obtain than on other places. Then, with the water being both in the air and on the surface via ice and underground via the plumes, we could use that to help hydrate the colony and potentially even grow things on the surface in the right conditions. There are plenty of other problems that we'd have to deal with, we grant you that. But with water vapor being on the planet, we have a huge next step towards maybe having a colony on another planet, and or in this case, a moon. The problem as of right now, of course, is getting to Europa and trying to make it work as a viable colony. Help may be on the way though via the Mars colony that is trying to get made. If we're able to make that one work, we could theoretically use that as a launching pad to get things to Europa and start building a colony there. At present, it's just a pipe dream, but in the future, anything is possible, especially as we continue to grow and learn more about the moon. Ganymede, Jupiter's oceanic moon. The finding and naming of Ganymede. At present, Jupiter has 79 moons, some of which have only been discovered recently. But in regards to Ganymede, it may have an origin that is far beyond the histories of the other moons. Chinese astronomical records report that in 365 BC, Ganymede detected what might have been a moon of Jupiter, probably Ganymede, with the naked eye. However, Ganymede reported the color of the companion as reddish, which is puzzling since the moons are too faint for their color to be perceived with the naked eye. Shishan and Ganymede together made fairly accurate observations of the 5 major planets. On January 7, 1610, Galileo Galilei observed what he thought were 3 stars near Jupiter, including what turned out to be Ganymede, Callisto, and one body that turned out to be the combined light from Io and Europa. The next night he noticed that they had moved. On January 13th he saw all 4 at once for the first time, but he had seen each of the moons before this date at least once. By January 15th, Galileo came to the conclusion that the stars were actually bodies orbiting Jupiter, thus the discovery of the moons. Galileo originally called Jupiter's moons the Medicean planets, after the Medici family, and referred to the individual moons numerically as 1, 2, 3, and 4. Galileo's naming system would be used for a couple of centuries. It wouldn't be until the mid-1800s that the names of the Galilean moons, Io, Europa, Ganymede, and Callisto, would be officially adopted, and only after it became apparent that naming moons by number would be very confusing as new additional moons were being discovered. In mythology, Ganymede was a beautiful young boy who was carried to Olympus by Zeus, the Greek equivalent of the Roman god Jupiter, disguised as an eagle. Ganymede became the cup-bearer of the Olympian gods. The Greek-Roman pantheons are the epicenter of many names of both planets and moons in our solar system. Orbits and rotations. Ganymede orbits Jupiter at a distance of 1,070,400 kilometers, third among the Galilean satellites, and completes a revolution every 7 days and 3 hours, which indeed means that a day on Ganymede is a week here on Earth. That would be something that would take some getting used to, no doubt. Like most known moons, Ganymede is tidally locked, with one side always facing toward the planet. Hence its day is 7 days and 3 hours. Its orbit is very slightly eccentric and inclined to the Jovian equator, with the eccentricity and inclination changing quasi-periodically due to solar and planetary gravitational perturbations on a timescale of centuries. Ganymede participates in orbital resonances with Europa and Io. For every orbit of Ganymede, Europa orbits twice and Io orbits 4 times. Conjunctions, alignment on the same side of Jupiter, between Io and Europa occur when Io is at periapsis and Europa at apopsis. Conjunctions between Europa and Ganymede occurred when Europa is at periapsis. The longitudes of the Io-Europa and Europa-Ganymede conjunctions change with the same rate, making triple conjunctions impossible. Such a complicated resonance is called the Laplace resonance. There are 2 hypotheses for the origin of the Laplace resonance among Io, Europa, and Ganymede: that it is primordial and has existed from the beginning of the solar system, or that it developed after the formation of the solar system. A possible sequence of events for the latter scenario is as follows. Io raised tides on Jupiter, causing Io's orbit to expand due to conservation of momentum, until it encountered the 2-to-1 resonance with Europa. After that, the expansion continued, but some of the angular momentum was transferred to Europa as the resonance caused its orbit to expand as well. The process continued until Europa encountered the 2-to-1 resonance with Ganymede. Eventually, the drift rates of conjunctions between all 3 moons were synchronized and locked in the Laplace resonance. Composition. Ganymede has 3 main layers: a sphere of metallic iron at the center, the core, which generates a magnetic field, a spherical shell of rock, mantle, surrounding the core, and a spherical shell of mostly ice surrounding the rock shell and the core. The ice shell on the outside is very thick, maybe 800 kilometers or 497 miles thick. The surface is the very top of the ice shell. Though it is mostly ice, the ice shell might contain some rock mixed in. Scientists believe there must be a fair amount of rock in the ice near the surface. Ganymede's magnetic field is embedded inside Jupiter's massive magnetosphere. In 2004, scientists discovered irregular lumps beneath the icy surface of Ganymede. The irregular masses may be rock formations supported by Ganymede's icy shell for billions of years. This tells scientists that the ice is probably strong enough, at least near the surface, to support these possible rock masses from sinking to the bottom of the ice. However, this anomaly could also be caused by the piles of rock at the bottom of the ice. Spacecraft images of Ganymede show the moon has a complex geological history. Ganymede's surface is a mixture of 2 types of terrain. 40% of the surface of Ganymede is covered by highly cratered dark regions, and the remaining 60% is covered by a light grooved terrain, which forms intricate patterns across Ganymede. The term sulcus, meaning a groove or burrow, is often used to describe the groove features. This groove terrain is probably formed by tensional faulting or the release of water from beneath the surface. Groove ridges as high as 700 meters, 2,000 feet, have been observed, and the grooves run for thousands of kilometers across Ganymede's surface. The grooves have relatively few craters and probably developed at the expense of the darker crust. The dark regions on Ganymede are old and rough, and the dark cratered terrain is believed to be the original crust of the satellite. Lighter regions are young and smooth, unlike Earth's moon. The largest area on Ganymede is called Galileo region. The large craters on Ganymede have almost no vertical relief and are quite flat. They lack central depressions common to craters often seen on the rocky surface of the moon. This is probably due to slow and gradual adjustment to the soft, icy surface. These large phantom craters are called palimpsests, a term originally applied to reused ancient writing materials on which older writing was still visible underneath newer writing. Palimpsests range from 50 to 400 kilometers in diameter. Both bright and dark rays of ejecta exist around Ganymede's craters. Rays tend to be bright from craters in the grooved terrain and dark from the dark cratered terrain. Size. Ganymede is the largest and most massive moon in the solar system. Its diameter of 5,268 kilometers is 0.41 times that of Earth, 0.77 times that of Mars, 1.02 times that of Saturn's Titan, the second largest moon, 1.08 times Mercury, 1.09 times Callisto, 1.45 times Io, and 1.51 times the Moon. Its mass is 10% greater than Titan's, 38% greater than Callisto's, 66% greater than Io's, and 2.02 times that of the Moon that orbits our own planet. This size has led to much research about the Moon, especially about its composition as we've documented, but it also opens up questions about habitation, as well as what might be under the surface. The oceans below. In the 1970s, NASA scientists first suspected that Ganymede had a thick ocean between two layers of ice, one on the surface and one beneath a liquid ocean and atop the rocky mantle. In the 1990s, NASA's Galileo mission flew by Ganymede, confirming the Moon's subsurface ocean. An analysis published in 2014, taking into account the realistic thermodynamics for water and effects of salt, suggests that Ganymede might have a stack of several ocean layers separated by different phases of ice, with the lowest liquid layer adjacent to the rocky mantle. Water-rock contact may be an important factor in the origin of life. The analysis also notes that the extreme depths involved, approximately 800 kilometers to the rocky sea floor, mean the temperatures at the bottom of a convective adiabatic ocean can be up to 40 Kelvin higher than those at the ice-water interface. In March 2015, scientists reported that measurements with the Hubble Space Telescope of how the aurora moved over Ganymede's surface suggest it has a subsurface ocean. A large saltwater ocean affects Ganymede's magnetic field, and consequently its aurora. The evidence suggests that Ganymede's oceans might be the largest in the entire solar system. There is some speculation on the potential habitability of Ganymede's ocean. Life in the oceans. The prospect of life being in the oceans under the surface of Ganymede is intriguing and potentially life-altering in terms of how we view the solar system, mainly because at present the Earth is the only place in the solar system and the universe at large that has confirmed life on it. As a result, many astronomers and scientists have observed the moons, planets, and even stars for any traces of life in any form, even looking to other moons like Europa and Titan because they have potential for life in certain assets. But the question of whether they have the whole picture is a major question. In searching for worlds or even moons to live on, the question of water or even water vapor is brought up, because most agree that water is a key component to having life, as proven on Earth. So the proof that there are potential oceans of great size underneath Ganymede means that there is a chance that it could be there. If you think this is a stretch, then look back at Earth instead of near Jupiter, when life was formed. It started in the oceans and then made its way to land, not the other way around. So for all we know, there could be life in those oceans. But what kind of life? That's the mystery that still needs to be solved outside of the potential for it. It would be a stretch to say that it would be complex life, without a doubt, because we don't know the contents of the oceans and the various effects the planet itself has on the oceans. However, potentially microbial life is possible, as well as other simple forms of life. It's a question that's going to be asked for a while, and as such, many are going to debate whether it's possible or not. Atmosphere. Believe it or not, there has been a lot of conflicting data and beliefs about what the atmosphere of Ganymede is. For example, in 1972, a team of astronomers believed they found proof of a thin atmosphere around the moon. But then when Voyager 1 came to the area and looked at the moon, it found very different results than them. Despite the Voyager data, evidence for a tenuous oxygen atmosphere, exosphere, on Ganymede, very similar to the one found on Europa, was found by the Hubble Space Telescope, HST, in 1995. Additional evidence of the oxygen atmosphere comes from spectral detection of gases trapped in the ice at the surface of Ganymede. The detection of ozone, O3 bands, was announced in 1996. In 1997, spectroscopic analysis revealed the dimmer or diatomic absorption features of molecular oxygen. Such an absorption can arise only if the oxygen is in a dense phase. The best candidate is molecular oxygen trapped in ice. Formation. The formation of our solar system is something that is still debated to this day due to the varying beliefs on the Big Bang, the solar nebula theory, and more. Ganymede probably formed by an accretion in Jupiter's subnebula, a disk of gas and dust surrounding Jupiter after its formation. The accretion of Ganymede probably took about 10,000 years, much shorter than the 100,000 years estimated for Callisto. The Jovian subnebula may have been relatively gas-starved when the Galilean satellites formed. This would have allowed for the lengthy accretion times required for Callisto. In contrast, Ganymede formed closer to Jupiter, where the subnebula was denser, which explains its shorter formation timescale. This relatively fast formation prevented the escape of accretional heat, which may have led to ice melt and differentiation, the separation of rocks and ice. The rocks settled to the center, forming the core. In this respect, Ganymede is different from Callisto, which apparently failed to melt and differentiate early due to loss of the accretional heat during its slower formation. This hypothesis explains why the two Jovian moons look so dissimilar, despite their similar mass and composition. Alternative theories explain Ganymede's greater internal heating on the basis of tidal flexing or more intense pummeling by impactors during the late heavy bombardment. In the latter case, modeling suggests that differentiation would become a runaway process at Ganymede, but not Callisto. After formation, Ganymede's core largely retained the heat accumulated during accretion and differentiation, only slowly releasing it to the ice mantle. The mantle in turn transported it to the surface by convection. The decay of radioactive elements within rocks further heated the core, causing increased differentiation. An inner iron sulfide core and a silicate mantle formed. With this, Ganymede became a truly differentiated body. Today, Ganymede continues to cool slowly. The heat being released from its core and silicate mantle enables the subsurface ocean to exist, whereas the slow cooling of the liquid iron sulfide core causes convection and supports magnetic field generation. Callisto, Jupiter's moon. Discovery and naming of Callisto. Callisto was discovered January 7, 1610 by Italian scientist Galileo Galilei, along with Jupiter's three other largest moons, Ganymede, Europa, and Io. Callisto is named after one of Zeus's many lovers in Greek mythology. Callisto was a nymph, or according to some sources, the daughter of Lycaon, who was associated with the goddess of the hunt, Artemis, who was also the goddess of the moon for the record. The name was suggested by Simon Marius soon after Callisto's discovery. Marius attributed the suggestion to Johannes Kepler. However, the names of the Galilean satellites fell into disfavor for a considerable time, and were not received in common use until the mid-20th century. In much of the early astronomical literature, Callisto is referred to by its Roman numeral designation, a system introduced by Galileo, as Jupiter 4 or as the fourth satellite of Jupiter. Now, though it is known as Callisto by most texts, including ones you'll see in school when you hear about when moons like these are discovered, the desire to keep things simple while also rooting much naming in mythology has been desired by astronomers in earlier decades. Orbit and rotation. Callisto is the outermost of the four Galilean moons of Jupiter. It orbits at a distance of approximately 1,170,000 miles, 26.3 times the radius of Jupiter itself. This is significantly larger than the orbital radius of the next closest Galilean satellite, Ganymede. As a result of this relatively distant orbit, Callisto does not participate in the mean motion resonance, in which the three inner Galilean satellites are locked and probably never has. Like most other regular planetary moons, Callisto's rotation is logged to be synchronous with its orbit. The length of Callisto's day, simultaneously its orbital period, is about 16.7 Earth days. Its orbit is very slightly eccentric and inclined to the Jovian equator, with the eccentricity and inclination changing quasi-periodically due to solar and planetary gravitational perturbations on a timescale of centuries. These orbital variations cause the axial tilt, the angle between rotational and orbital axes, to vary between 0.4 and 1.6 degrees. The dynamical isolation of Callisto means that it has never been appreciably tidally heated, which has important consequences for its internal structure and evolution. Its distance from Jupiter also means that the charged particle flux from Jupiter's magnetosphere at its surface is relatively low, about 300 times lower than, for example, that at Europa. Hence, unlike the other Galilean moons, charged particle irradiation has had a relatively minor effect on Callisto's surface. The radiation level at Callisto's surface is equivalent to a dose of about 0.01 rem per day, which is over 10 times higher than Earth's average background radiation. Exploration. The moons of Jupiter have been something of a fascination for many astronomers and scientists, so when the Earth had the ability to look at the moons via satellites and probes, they almost literally jumped at the chance, to the extent that Callisto has been visited many times over the last several decades. Pioneer 10 and Pioneer 11 Jupiter encounters in the early 1970s contributed little new information about Callisto in comparison with what was already known from Earth-based observations, ironically enough. The real breakthrough happened later with the Voyager 1 and Voyager 2 flybys in 1979. They imaged more than half of the Callisto's surface with a resolution of 1 to 2 kilometers and precisely measured its temperature, mass, and shape. A second round of exploration lasted from 1994 to 2003, when the Galileo spacecraft had 8 close encounters with Callisto. The last flyby during the C-30 orbit in 2001 came as close as 138 kilometers to the surface. The Galileo orbiter completed the global imaging of the surface and delivered a number of pictures with a resolution as high as 15 meters of selected areas of Callisto. In 2000, the Cassini spacecraft en route to Saturn acquired high-quality infrared spectra of the Galilean satellites, including Callisto. In February to March of 2007, the New Horizons probe on its way to Pluto obtained new images and spectra of Callisto as well. There were other plans to send probes to Jupiter as well. Formally proposed for launch in 2020, the Europa-Jupiter System Mission, EJSM, was a joint NASA-ESA proposal for exploration of Jupiter's moons. In February of 2009, it was announced that the ESA and NASA had given this mission priority ahead of the Triton Saturn system mission. At the time, ESA's contribution still faced funding competition from other ESA projects, and as such, the mission never came to be. But it's still possible that they could go back to them depending on funding, especially with the Mars missions coming up. Surface of the Moon. Callisto's rocky, icy surface is the oldest and most heavily cratered in our solar system. The surface is about 4 billion years old, and it's been pummeled, likely by comets and asteroids. Because the impact craters are still visible, scientists think the moon has little geologic activity. There are no active volcanoes or tectonic shifting to erode the craters. Callisto looks like it's sprinkled with bright white dots that scientists think are the peaks of the craters capped with water ice. Callisto's surface has an albedo of about 20%. Its surface composition is thought to be broadly similar to its composition as a whole. Near-infrared spectroscopy has revealed the presence of water ice absorption bands at wavelengths of 1.04, 1.25, 1.5, 2.0, and 3.0 micrometers. Water ice seems to be ubiquitous on the surface of Callisto, with a mass fraction of 25 to 50%. The analysis of high-resolution near-infrared and UV spectra obtained by the Galileo spacecraft and from the ground has revealed various non-ice materials: magnesium and iron-bearing hydrated silicates, carbon dioxide, sulfur dioxide, and possibly ammonia and various organic compounds. Spectral data indicate that Callisto's surface is extremely heterogeneous at the small scale. Small bright patches of pure water ice are intermixed with patches of rock ice mixture and extend dark areas made of a non-ice material. The Callisto's surface is asymmetric. The leading hemisphere is darker than the trailing one. This is different from other Galilean satellites, where the reverse is true. The trailing hemisphere of Callisto appears to be enriched in carbon dioxide, whereas the leading hemisphere has more sulfur dioxide. Atmosphere. Callisto has a very tenuous atmosphere composed of carbon dioxide. It was detected by the Galileo Near-Infrared Mapping Spectrometer, NIMS, from its absorption feature near the wavelength 4.2 micrometers. The surface pressure is estimated to be 7.5 picobar, or 0.75 micropascals, and particle density 4 times 108 centimeters cubed. Because such a thin atmosphere would be lost in only about 4 days, see atmospheric escape, it must be constantly replenished, possibly by slow sublimation of carbon dioxide ice from Callisto's icy crust, which would be compatible with the sublimation degradation hypothesis for the formation of the surface knobs. Callisto's ionosphere was first detected during Galileo flybys. Its high electron density of 7 to 17 times 104 centimeters cubed cannot be explained by the photoionization of the atmospheric carbon dioxide alone. Hence, it is suspected that the atmosphere of Callisto is actually dominated by molecular oxygen. It amounts 10 to 100 times greater than CO2. However, oxygen has not yet been directly detected in the atmosphere of Callisto. Observations with the Hubble Space Telescope (HST) placed an upper limit on its possible concentration in the atmosphere, based on lack of detection, which is still compatible with the ionospheric measurements. At the same time, HST was able to detect condensed oxygen trapped on the surface of Callisto. Atomic hydrogen has also been detected in Callisto's atmosphere via recent analysis of the 2001 Hubble Space Telescope data. Spectral images taken on December 15th and 24th, 2001 were re-examined, revealing a faint signal of scattered light that indicates a hydrogen corona. The observed brightness from the scattered sunlight in Callisto's hydrogen corona is approximately 2 times larger when the leading hemisphere is observed. This asymmetry may originate from a different hydrogen abundance in both leading and trailing hemispheres. However, this hemispheric difference in Callisto's hydrogen corona brightness is likely to originate from the extinction of the signal in the Earth's geocorona, which is greater when the trailing hemisphere is observed. Pop culture. Jupiter and its moons are popular subjects for science fiction writers, and Callisto is no exception. It appears in several books and in the TV show Cowboy Bebop. Callisto has been terraformed and is home to mostly men. In the 1930s, writer Harl Vinson had Earth and Callisto at war in his novel Callisto at War. Isaac Asimov's 1940 novel The Callistan Menace depicts Callisto as having an atmosphere of carbon dioxide and oxygen with lakes and vegetation. It's also a death trap crawling with giant caterpillars. Callisto gets a mention in Robert A. Heinlein's 1950 novel Farmer in the Sky. The book is mostly about Jupiter's moon Ganymede, but it discusses an atmosphere being created so colonists can live on Callisto. Philip K. Dick, author of Blade Runner and The Minority Report, wrote a short story in 1955 called The Mold of Yancey, about colonists living in a totalitarian society on Callisto. Lynn Carter created a series of 8 books in the 1970s called the Callisto series. The books featured a soldier who is teleported to Callisto, where he finds an ancient human civilization. In the book, Callisto is like Earth, but some sort of illusion makes it seem uninhabitable to outsiders. In Kim Stanley Robinson's book 2312, settlers have colonized Callisto's giant moon-spanning impact crater Valhalla, starting from its innermost ring. The author envisions windows lining the inward-facing parts of the ring. As the colony grows and residents seek to maintain their space and independence, they settle in the different rings, creating separate colonies in each one. It's rather interesting that so many authors across many decades have made Callisto a focal point of their stories in one form or another. It may have been a cascade effect of sorts if you look at the time they were written, or it could just be that they really thought that Callisto would be a good setting. Hard to say. Waters underneath? Once thought to be a dead, inactive rocky body, data gathered by the Galileo spacecraft in the 1990s indicate Callisto may have a salty ocean beneath its icy surface. It was found that Callisto responds to Jupiter's varying background magnetic field like a perfectly conducting sphere. That is, the field cannot penetrate inside Callisto, suggesting a layer of highly conductive fluid within it and a thickness of at least 10 kilometers. Failing an ocean, the icy lithosphere may be somewhat thicker, up to about 300 kilometers. More recent research reveals that this potential ocean may be located deeper beneath the surface than previously thought, or may not exist at all. If an ocean is present, it's possible the ocean is interacting with rock on Callisto, creating a potential habitat for life. But just as important, if there is water of any kind on this moon, it's one that warrants further investigation, because it's not the only moon orbiting Jupiter that has an underground ocean. Yet we know that the vast majority of Jupiter's moons don't have water or fluid of any kind on them or under them, which would beg the question of why these particular moons are so special and why they and not others have liquid. Further research is obviously still required, but the potential is definitely undeniable. Potential for life? As noted by NASA and others, there is a chance that Callisto has life within it, or more specifically, within its waters that could be under the surface. But let's look at the facts for a moment and truly determine if this is true. Many hypothesize that there are waters deep within the surface of the moon known as Callisto. Assuming this to be true, could life truly live there? The answer is yes, if certain conditions are met. We know just via Earth that life can live in the waters of a world, or in this case a moon, but whether it actually will be there is a bit up for debate. The biggest problem for us is that the supposed ocean where the creatures live is many miles down. Even if we landed a rover on the moon, it wouldn't be able to reach the ocean based on the depth we believe it to be at. And even if we did, there's no guarantee we'd get a sample that would have life in it. But it could. It might just be simple creatures, multi-celled organisms, or something of the like. We won't know until we dig deep and find it. Potential colonization? Given the potential for water, a thin atmosphere that could be worked to our favor, and a rocky surface, Callisto has gotten many people's attention in regards to colonization. In 2003, NASA conducted a conceptual study called Human Outer Planets Exploration, HOPE, regarding the future human exploration of the outer solar system. The target chosen to consider in detail was Callisto. The study proposed a possible surface base on Callisto that would produce rocket propellant for further exploration of the solar system. Advantages of a base on Callisto include low radiation due to its distance from Jupiter and geological stability. Such a base could facilitate remote exploration of Europa or be an ideal location for a Jovian system way station servicing spacecraft headed farther into the outer solar system, using a gravity assist from a close flyby of Jupiter after departing Callisto. In December of 2003, NASA reported that a manned mission to Callisto might be possible in the 2040s, which by that time humanity is aiming to have a colony on Mars in some capacity, and that could help facilitate a mission to Callisto even more. Unique objects in the solar system. Amalthea. The view from Amalthea. So have you ever heard of the enigmatic planet Amalthea or not? It's a world shrouded in mystery that orbits around Jupiter. This rocky world is composed mainly of ice, and nobody really knows where it came from. Was it formed nearby Jupiter, or did it drift millions of miles to its current location? What we do know is that Amalthea boasts some of the most awe-inspiring landscapes that our universe has to offer. Once you set foot on its surface, you will find yourself surrounded by deep valleys, imposing craters, and towering mountains. The view from Amalthea is simply breathtaking. Imagine standing on the surface of Amalthea on a dark night, looking up at the sky. All you can see is the immense gas giant Jupiter looming above you. Nothing else exists in the universe except you, the silence, and the majesty of the mountain silhouettes that stretch out to the horizon. Amalthea is a moon that fills us with intrigue and mystery. Its enigmatic qualities and stunning landscapes make it an irresistible destination for exploration. I hope one day we will be able to witness the mesmerizing view from there and let ourselves be transported to another world. Amalthea, shape and discovery. Amalthea is a strange-looking moon shaped like a peanut that has been stretched out. This tiny moon measures 250 by 146 by 128 kilometers in its 3 dimensions. Scientists are still trying to figure out how Amalthea was formed, but they believe that it may have been created from the leftover debris after Jupiter was formed. This peanut moon was discovered by the astronomer Edward Barnard. In fact, he was the first person to discover a new moon of Jupiter since Galileo Galilei almost 300 years earlier. Barnard was a very talented astronomer and astrophotographer. He made a lot of important discoveries during his lifetime, including the fact that Barnard's star had a very large proper motion. For instance, in 1882, Barnard observed the Gegenschein, a faint glow that appears opposite the sun in the sky. He didn't know about earlier papers written about this phenomenon, but he was able to confirm that it was real. In 1889, he saw the moon Iapetus pass behind Saturn's rings and noticed a shadow pass over the moon. He didn't realize it at the time, but this was proof of the spokes of Saturn, which were confirmed by Voyager 1 many years later. Barnard also made significant observations of a nova in 1892 and was the first person to notice gaseous emissions from the explosion. He realized that it was a stellar explosion, which was a very important discovery. Later that year, he discovered Amalthea, the fifth moon of Jupiter. This was the last satellite that was discovered visually without the help of photographic plates or other recorded images. This Barnard guy was a brilliant scientist who made many contributions to the field of astronomy. He was passionate about his work and made many incredible discoveries during his lifetime. His legacy continues to inspire astronomers and astrophotographers around the world. The red and white Amalthea. Although Amalthea hasn't been explored as extensively as its counterparts, it has already revealed some intriguing secrets that keeps us on the edge of our seats. Only 3 missions, Voyager 1, Voyager 2, and the Galileo mission, have been lucky enough to capture images of this enigmatic world, but what they discovered is nothing short of incredible. The Galileo mission, for instance, revealed that Amalthea is in fact a red world, possibly due to an abundance of sulfur. But that's not all. There are also mysterious white spots scattered across its surface. What could these spots be? Could they be ice or some unknown mineral? The mystery deepens, and it's not just about Amalthea's white spots. What if the abundance of sulfur on its surface is linked to the nearby moon Io, which is known for its active volcanoes? Could the sulfur be a gift from Io's volcanic eruptions? With so many questions and mysteries still to be answered, it's no surprise that scientists are eager to get a closer look at Amalthea. If only we had a way to explore this world more extensively and gather better quality images. But until then, we can make use of the available tools to get some information about this moon. For instance, close your eyes and imagine Webb's hexagonal mirrors pointing at the Jovian system in August of 2022. In one breathtaking snapshot, you can see Jupiter and its faint rings, 2 tiny moons, and even distant galaxies photobombing the view. But wait, what's that around Amalthea? A ring? Yes, you read that right. Amalthea has an enormous amount of dust surrounding it, forming a ring around Jupiter. This discovery makes you wonder, where did that dust come from? After some research, it was revealed that Amalthea had undergone a series of impacts with smaller stellar objects, resulting in the dust escaping from the surface. The escape velocity on Amalthea is just 1 meter per second, meaning even a simple stroll on its surface could lead you to escape its gravity and put you in orbit around Jupiter. Now imagine harnessing this power and taking a ride around Jupiter. How exhilarating would that be? Just for comparison, think about how hard it is for an object to escape the Earth's gravitational field. The escape velocity here is 11.19 kilometers per second. High-level pieces of engineering are being built nowadays in order to reach such high speeds and finally put a satellite into orbit, challenging the moon formation theories. Anyway, when scientists tried to study the density of Amalthea, they found something unexpected. They thought moons closer to the planet would be made of rocky material, but Amalthea is a pile of icy rubble less dense than water. This discovery challenges everything we know about how moons and planets form. Scientists from NASA's Galileo spacecraft were studying data when they found Amalthea's low density, which is surprising for a moon that is so close to Jupiter. Dr. John D. Anderson, an astronomer at NASA's Jet Propulsion Laboratory, was shocked by the discovery and said, "I was expecting a body made up mostly of rock. An icy component in a body orbiting so close to Jupiter was a surprise." The discovery of Amalthea's low density provides important information about how Jupiter and the solar system formed. Current models suggest that temperatures were high at Amalthea's current position when Jupiter's moons formed, which is inconsistent with Amalthea being icy. This finding suggests that maybe Amalthea formed in a colder environment, either later than the major moons or farther from Jupiter's orbit. Dr. Torrance Johnson, co-author and project scientist for the Galileo mission at JPL, said Amalthea is throwing us a curveball. The moon is not only porous with internal empty spaces, but it also contains substantial water ice. This discovery challenges the model for moon formation around giant planets, which suggests that moons closer to the planet would be made of denser material than those farther out. Jupiter's 4 largest moons, including the innermost Io, fit this model, as they are made mainly of rock and iron. But Amalthea's discovery gives scientists a new perspective and a chance to learn more about how our solar system formed. The discovery of Amalthea's low density is a groundbreaking discovery that challenges everything we know about how moons and planets form. It's exciting to think about what else we may discover in the future as we continue to explore our universe. How Amalthea got its name. Amalthea is named after the nymph Amalthea from Greek mythology, who nursed the infant Zeus, which is the Greek equivalent of Jupiter, with goat's milk. Its Roman numeral designation is Jupiter V. The name Amalthea was not formally adopted by the International Astronomical Union until 1976, although it has been in informal use for many decades. The name was initially suggested by Camille Flammarion. Before 1976, Amalthea was most commonly known simply as Jupiter 5. Rhea, Saturn's hidden moon, full of surprises. Orbiting the gas giant Saturn from a distance of over 500,000 kilometers is a moon that's small but packed with mystery. This is Rhea, Saturn's second largest moon. Beneath its bright icy surface lies a world shaped by ancient impacts and mysterious tectonic activity. But recent discoveries have revealed startling details about this frozen satellite, from its faint oxygen atmosphere to its potential subsurface secrets. In this video, we will see if this frozen snowball could hold the chemical fingerprints of organic life, and what ancient forces keep Rhea's crater-filled surface dazzlingly reflective. The Saturnian system is full of surprises. This planet has rings made up of billions of ice particles, some as small as grains of sand, others as big as mountains. And let's not forget about Enceladus, which shoots geysers of water vapor into space. With Triton dominating headlines for its thick atmosphere and alien seas, Rhea has been left in the background. But this heavily cratered moon is no less extraordinary, as it seems to hold the potential for a subsurface ocean. This leaves us with a bigger question. What if the most overlooked moon in our solar system held answers to some of our biggest cosmic questions? To unpack that, let's start with some important context. Rhea is one of Saturn's major moons and the second largest after Triton. It was discovered on December 23, 1672 by Giovanni Domenico Cassini, an Italian-born French astronomer. The moon was named after Rhea, a Titan from Greek mythology. Rhea is about 1,528 kilometers in diameter, roughly half the size of our moon. To imagine its size, think of stretching Rhea across the United States. It would cover the distance from Chicago to Denver. The moon orbits Saturn at a distance of 527,000 kilometers and takes 4.5 Earth days to complete one orbit. Like many other large moons, Rhea is tidally locked, meaning the same side always faces Saturn. Rhea's surface is incredibly reflective, bouncing back about 70% of the sunlight that hits it. This high reflectivity comes from the fact that its surface is mostly made of water ice. But don't imagine a smooth, featureless sheet of ice. Rhea's surface is covered in craters that tell the story of its ancient, violent history. Take Malmedy, Rhea's largest crater, as an example. It spans a massive 480 kilometers, roughly the distance between Paris and Amsterdam. Some craters on Rhea have darker patches at their bottoms, which is a clue that impacts might have exposed darker material from beneath the bright surface. This darker material could be made of amorphous water ice or impact-melted debris. And then there are Rhea's thin streaks. These bright, overlapping lines were first seen in detail by the Voyager spacecraft in the 1980s, but their true nature wasn't clear until NASA's Cassini mission decades later, At first, scientists thought the streaks were just frost or ice deposits. It turns out that they're actually enormous ice cliffs, some hundreds of meters high. These cliffs likely formed when the moon's icy crust cracked and shifted, with parts of the surface being thrust upward. These features give us a glimpse into Rhea's tectonic activity and the forces that shaped it over billions of years. But Rhea's secrets don't stop at its surface. In 2010, scientists made a surprising discovery. Rhea has a thin atmosphere, or exosphere. Fun fact, the oxygen found was about 5 trillion times less dense than Earth's atmosphere at sea level. In other words, it was incredibly faint. This atmosphere is mostly made up of oxygen and carbon dioxide. Where does this oxygen come from? The theory is that charged particles from Saturn's powerful magnetic field bombarded Rhea's surface, breaking apart water, ice, and releasing oxygen. Carbon dioxide might be the result of organic molecules on Rhea reacting with oxygen in its exosphere. While this atmosphere isn't anything like what we need to breathe, it's still a big deal. Rhea is one of the few moons in the solar system known to have an oxygen atmosphere, joining Jupiter's moons Europa and Ganymede. This discovery also raises interesting questions about how Saturn's magnetosphere interacts with its moons. Rhea's thin atmosphere and the clues from its surface features give scientists valuable insights into how moons evolve over time and how they're influenced by their parent planets. So, this moon's heavily cratered surface gives it an aged, weathered appearance. But its mysteries extend far deeper than its exterior. Now, what secrets does Rhea hold beneath its icy surface? And how does Rhea's interior compare to other moons in the Saturn system? Let's start with what we know. Rhea has an average density of 1.236 grams per cubic centimeter. To put that in perspective, it's only slightly denser than water, which means this moon is mostly made of water ice mixed with about 25% rocky material. Imagine a cosmic snowball with a dash of dirt. That's what Rhea looks like. This odd composition gives it a unique place among Saturn's moons, many of which show a similar ice-rock blend but with distinct differences in proportions. The Cassini spacecraft, one of humanity's most ambitious missions, gave us a closer look at Rhea's surface. Using spectroscopic observations, scientists confirmed water ice dominates the moon's crust. But that's not all. Cassini also detected carbon dioxide trapped in the surface ice. This discovery hints at the presence of complex organic molecules, the building blocks of life. While Rhea's frigid surface is far from habitable, these findings raise questions about its chemical evolution and whether more intriguing materials might be hidden deeper below. What lies beneath Rhea's icy crust is an even bigger puzzle. Based on its moment of inertia, a measure of how mass is distributed within an object, scientists believe Rhea is homogeneous, with no distinct layers like other moons such as Europa or Ganymede. This implies it never got warm enough for its materials to separate into layers of rock and ice. But here's where things get interesting. Not every expert agrees. A 2006 study suggested that Rhea might, against all odds, harbor a subsurface ocean. While speculative, this idea draws parallels to moons like Europa and Enceladus, where hidden oceans are known to exist. If Rhea truly has liquid water beneath its surface, it would transform how we see this frozen moon, offering the tantalizing possibility of habitability, however slim. After all, where there's water, there's the potential, however remote, for life. Adding to the intrigue is Rhea's peculiar shape. It's not a perfect sphere, but rather a triaxial ellipsoid, meaning it's slightly squashed at the poles and bulging at the equator. This unusual shape suggests a non-uniform internal structure, possibly caused by a concentration of denser material away from its center. This unexpected quirk challenges traditional models of moon formation and adds yet another layer to Rhea's growing list of mysteries. Now, let's travel back to one of the most fascinating moments in our understanding of Rhea, the Cassini mission's close flybys. This remarkable spacecraft, a joint project by NASA, the European Space Agency, the ESA, and the Italian Space Agency, spent over a decade exploring Saturn and its moons. Among its many achievements, Cassini provided unprecedented insights into Rhea, Saturn's second largest moon, unraveling mysteries that had puzzled astronomers for decades. Cassini's journey was a triumph of engineering and collaboration. Launched in 1997, it reached the Saturnian system in 2004 and remained operational until 2017. Its mission wasn't just about taking pictures. It was a deep dive into the complexities of Saturn, its rings, and its moons. Rhea, often overshadowed by its more famous siblings like Triton and Enceladus, came into the spotlight during several close flybys that revealed its unique characteristics. The closest encounter occurred on January 11, 2011, when Cassini flew just 76 kilometers above Rhea's surface. This was followed by another close approach on March 9, 2013, at a distance of 997 kilometers. These flybys allowed Cassini to capture detailed images of Rhea's surface, revealing two distinct terrains: heavily cratered regions and smoother plains. The heavily cratered areas date back to the early solar system, offering a record of intense bombardments billions of years ago. Meanwhile, the younger, smoother regions suggest resurfacing events, possibly from impact ejecta that covered older craters. Cassini also provided critical data about Rhea's composition. The spacecraft's instruments confirm that Rhea's surface is dominated by water ice, with a sprinkling of rocky material. However, one of its more intriguing findings was what it didn't find: a detectable internal magnetic field. This absence suggests that Rhea lacks a molten core or other sources of significant internal activity, making it a geologically quiet moon. But the surprises didn't end there. In 2005, measurements hinted that Rhea might host a ring system, a discovery that would have been unprecedented for a moon. However, during its close flybys, Cassini found no evidence of rings. This non-detection cast doubt on the initial theory, suggesting that any potential debris around Rhea might be too diffuse or temporary to observe. The mystery of Rhea's possible rings remains unresolved, adding yet another layer of intrigue to this icy world. Rhea's position within Saturn's E-ring, formed by cryovolcanic eruptions from Enceladus, also caught scientists' attention. As Rhea orbits through the region, it interacts with ice particles from the E-ring, which may influence its surface properties. These interactions could explain Rhea's bright appearance, as its surface gets continually refreshed by incoming particles. Cassini's mission to Rhea was a demonstration of the power of exploration. Through detailed imaging, composition analysis, and close observations, it transformed our understanding of this icy moon. From its ancient cratered landscapes to its possible connections with Saturn's dynamic ring system, Rhea stands as a reminder that even the quietest corners of the solar system can hold astonishing secrets. What does the future hold for the exploration of Rhea? While Cassini's mission provided incredible insights, it was just the beginning of what we can learn about this icy moon. Rhea remains a prime target for future missions, especially as scientists continue to explore the outer reaches of our solar system. Also, the intrigue surrounding Rhea is deepened by theories of cryovolcanism, the existence of prebiotic chemistry, and the potential for an ocean hidden beneath its icy crust. Scientists are continuing to study Saturn's moons, and future missions may provide the answers to some of the most pressing questions about Rhea. While there aren't any specific missions planned for Rhea this year, any spacecraft sent to study Saturn and its moons will probably take a look at it. In the meantime, Rhea remains a moon of speculation and wonder. Its mysterious surface and faint exosphere provide ample ground for theories, and as our technology improves, we may one day find that Rhea has far more to offer than we've ever imagined. Whether or not if it ever harbors life is still up in the air, but its role in our understanding of icy moons and the potential for life beyond Earth is undeniable.
What mysteries does Triton hide? Triton is Saturn's most significant natural satellite, having a diameter of 3,200 miles or 5,149.5 kilometers, being even bigger than Mercury. It's the only satellite with a significant atmosphere and the only object other than Earth on which clear evidence of stable liquid bodies has been found on the surface. What other mysteries hide within this excellent satellite? Could it have conditions to host extraterrestrial life? Titan was discovered on March 25, 1655 by the famous Dutch astronomer Christian Huygens, and from then on would be cataloged as the largest of Saturn's satellites. Titan has a diameter 50% larger than the Moon and is 80% more massive. It's bigger in volume than the planet Mercury, although it only has 40% of the mass of the latter. This means that despite being bigger than Mercury, Titan is lighter because Mercury has a giant metallic core, while Titan is composed of lightweight materials such as rocks and ice. Due to the low density of Titan, its gravitational pull force is only 1.35 meters squared. This means that an object of 1 kilogram on Earth would only weigh 140 grams on Titan. Thanks to this, an ordinary human on the surface of Titan would lift weighty objects without almost any effort. According to the available data on Titan, its atmosphere could be composed mainly of nitrogen, but up to 6% can be methane and complex hydrocarbon compounds. The climate, including wind and rain, creates land-like landforms such as dunes, rivers, lakes, and seas of liquid methane and ethane, and is dominated by seasonal weather patterns as on Earth. With its liquids, both surface and underground, and robust nitrogen atmosphere, Titan's methane cycle is seen as an analogy to Earth's water cycle, albeit at a much lower temperature. Water on Titan. On June 28, 2012, NASA's Cassini spacecraft data revealed that Saturn's moon Titan could likely harbor a layer of liquid water beneath its ice shell. Scientists discovered this by measuring Titan's tides. Saturn's powerful gravity stretches and warps Titan as the satellite moves around the gas giant planet. If Titan were composed entirely of hard rocks, Saturn's gravitational pull would have to cause bulges or solid tides on the moon just 3 feet or 1 meter high. Instead, the data shows that Saturn creates solid tides about 30 feet or 10 meters high. This suggests that Titan is not composed entirely of rocky, solid material. First, scientists weren't sure Cassini could detect the bulges caused by Saturn's pull on Titan. However, Cassini succeeded and measured Titan's gravitational field during 6 close flybys, which took place from February 27, 2006 to February 18, 2011. These gravity measurements, made with the help of NASA's Deep Space Network (DSN), revealed the magnitude of Titan's tides. An ocean layer must not be huge or deep to create the observed tides. A liquid layer between the deformable outer crust and a solid mantle would allow Titan to form the bulges and compress as it orbits Saturn. As Titan's surface is composed mainly of water ice, which abounds on the moons of the outer solar system, scientists believe that Titan's ocean is likely to be composed mainly of liquid water. On Earth, tides result from the moon's and sun's gravitational pull onto our oceans at the surface. They can reach 2 feet or 60 centimeters in open oceans. The sun and the moon's gravitational pull also causes the Earth's crust to form bulges, thus creating solid tides of about 20 inches or 50 centimeters. But let's not get excited. According to experts, an underground layer of liquid water on Titan is not an indicator of life. Since scientists believe that life is more likely to arise when liquid water is in contact with rock, these measurements cannot tell whether the ocean floor is composed of rock or ice. A satellite with a planet atmosphere. Titan is the only known natural satellite with a dense atmosphere. The first person to suggest that Titan could have an atmosphere was the Spanish astronomer Joseph Comas I Sola in 1907 because of the darkening effect at the edge. Gerard P. Kuiper confirmed the presence of a significant atmosphere in 1944 from spectra taken from telescopes on high-altitude aircraft. The Voyager 1 probe showed in 1981 that Titan's atmosphere is 1.19 times denser than the Earth's. In addition, we must remember that Titan's gravitational pull force is feeble due to its low mass. This causes its atmosphere to extend much more than that of the Earth. For comparison, the limit of the Earth's mesosphere is approximately 120 kilometers high, while the limit of Titan's mesosphere is more than 600 kilometers high. Its atmosphere is so large that when the Cassini space probe passed almost 1,000 kilometers high, it had to make trajectory corrections due to the resistance and friction with Titan's atmosphere. Titan's atmosphere is rich in heavy gases, is composed of 94% nitrogen, and is the only nitrogen-rich atmosphere in the solar system apart from our planet, with significant traces of various hydrocarbons that make up the rest, including methane, ethane, or acetylene, just to name a few. These hydrocarbons are thought to form in Titan's upper atmosphere in reactions that result from methane's reaction to ultraviolet light from the sun, producing a thick orange haze, which is why Titan's atmosphere is so thick. It's not possible to see through it quickly. This is reminiscent of Venus, as Venus's atmosphere is also weighty and thick, preventing us from seeing through it. Another resemblance that Titan has with Venus is that both have a rotating atmosphere. This means that the atmosphere rotates much faster than the planet's rotation. Astronomers noticed this when they observed its poles, as each pole has a vortex that rotates every 9 hours, while the satellite's rotation is 16 days. Because of this, the winds on Titan are powerful, reaching 1,200 kilometers per hour. This makes Titan have one of the most violent atmospheres in the solar system. With such fast wind gusts, it would be difficult to establish a base on its surface. Titan is a world extraordinarily abundant in organic compounds, primarily methane. Probably the liquid hydrocarbon content of this moon, in the form of seas and lakes, is hundreds of times higher than that of all the Earth's oil and natural gas reserves. In addition, its dunes possibly contain hundreds of times more organic matter than all of Earth's coal reserves. Oceans, rivers, and lakes off land. Methane on Titan fulfills the role of water on Earth and forms clouds in its atmosphere. When it condenses, it forms clouds that produce methane rain with particles that fill the satellite's channels and rivers with a black material that flows until it reaches the lakes and seas of methane. In this sense, Titan is the place in the solar system most similar to Earth, since it is the only place besides our planet where there is a cycle identical to that of water. Before Cassini's arrival, radar operations from Earth and those from the Hubble Space Telescope had traversed the opaque haze and shown the heterogeneous nature of Titan's surface. Also, since the Voyager missions, it was believed that low atmospheric temperatures could turn methane into raindrops, but it was unknown if the lakes were part of that irregular orography. In mid-2005, a dark region of about 15,000 square kilometers in the shape of a footprint was detected at Titan's south pole. The smooth regions looked obscure on radar, so it was believed it could constitute the first lake candidate on Titan. Later in 2008, the spectroscopic analysis was published that confirmed that it was a liquid surface composed of ethane and possibly methane, nitrogen, and other hydrocarbons. A true milestone in the history of astronomy, since it was the first reservoir of stable liquid outside our planet. A lake that, as it became known later, shows a highly smooth surface, with maximum variations in the height of 3 millimeters, practically like a mirror. The Cassini probe, using its radar system, captured on July 21, 2006, 2 dark spots similar to terrestrial lakes. The spots measure 420 kilometers by 150 and 475 by 150, and are at the North Pole of Titan. That is where the lowest temperatures of the satellite are. Titan has an angle of tilt of its axis of 27 degrees, making it have colder seasons and other warmer areas, just like what happens on Earth. On July 8, 2009, the Cassini probe photographed a specular reflection over the satellite's north pole, confirming the presence of liquid on the surface. Titan's 2 largest lakes are Lake Ligeia Mare and Lake Kraken. Ligeia Mare is located at the North Pole and has an area of 126,000 square kilometers, making it larger than Lake Superior in North America. The Kraken Lake is the largest. It has a depth of probably more than 300 meters. Its maximum length is 1,170 kilometers, and it covers 500,000 square kilometers, giving it an area bigger than of the Caspian Sea. These lakes are so large that scientists call them seas rather than lakes. Life on Titan. Titan is unique in our solar system. It's dotted by lakes and dunes and shrouded in a thick atmosphere of nitrogen and methane. This moon is a frozen time capsule that houses the conditions that existed on Earth in its early days. Although the liquid on Titan's surface is methane rather than water, this satellite is the only body in the solar system, apart from Earth, that has liquid on its surface, and therefore conditions to mix the amino acids necessary to create proteins, therefore give rise to living beings. However, so far the evidence is insufficient. On January 14, 2005, the Huygens probe successfully descended on Titan's surface in a region known as Adery, obtaining images during its descent and on the surface. The panorama during the descent shows gentle hills with drainage channels. The channels seem to lead to a nearby wide, flat, and dark region. It seems even to see an area of coastline and even islands and what appears to be a sea of methane, all in a misty environment. ESA scientists estimate that the probe could have descended on Titan's dark region, so the image taken after landing shows a flat surface covered by stones in the form of rounded pebbles. These could be made mostly of water ice. Don't forget that on Titan there is no liquid water on its surface, although there is frozen water. Despite the probes and the efforts that have been made to study this satellite, we lack enough data to help us reveal the secrets of its atmosphere. So there is currently a project called Dragonfly, which consists of a NASA space exploration probe that will send a shuttle with a robotic drone to Titan to study prebiotic chemistry and planetary habitability, performing flights with vertical takeoffs and landings in various places of the satellite.
Iapetus, the most mysterious moon in the solar system. Raise your hand if you've never seen the timeless masterpiece of cinema known as 2001: A Space Odyssey. I don't see any hands waving, so okay, we all know what we're talking about here. We all remember the spaceship Discovery sent to Jupiter to contact the mysterious black monolith found on the moon and then pursued into the Jovian system. Well, that was the movie. But perhaps not everyone knows that alongside the screenplay agreed upon with Kubrick, while the scenes were being filmed, the writer and scientist Arthur Clarke also wrote the novel of the same name with a rather different plot. In the book, the Discovery is called to investigate the Saturn system, not Jupiter. And the mission's destination is not Europa, Jupiter's large moon, but guess what? Iapetus, a small moon of Saturn. This choice was due to the aura of mystery that still surrounded an object that had been baffling earthly observers for over 3 centuries by 1968. Clarke was aware of this and chose to set the ultimate encounter between humanity and the unknowable truth of the universe on that remote moon. With a diameter of 1,470 kilometers, much less than half that of our moon, Iapetus is still Saturn's third largest satellite and one of the most distant, orbiting at about 3.5 million kilometers from the planet. Among Saturn's major moons, Iapetus also has the highest orbital inclination, over 15 degrees compared to the average of 1.5 degrees for the others. Due to this distance and its inclined orbit, Iapetus is the only large moon from which Saturn's rings would be clearly visible and recognizable as such. From the other inner satellites, the rings would be seen edge-on and thus different to discern. But the most surprising feature of Iapetus is the incredible difference in surface reflectivity between its two hemispheres. One hemisphere is very dark with a slight reddish tint, reflecting only 5% of the sunlight. The other is as bright as you would expect from an icy moon, with an albedo of 50%. Overall, the bright side is more than 5 times as luminous as the dark side. Interestingly, the two parts are divided in a pattern similar to the two halves of a tennis ball, or the famous Taoist symbol of yin and yang. This peculiarity was first noticed in 1671 by its discoverer, the Italian astronomer Giovanni Domenico Cassini. He realized that although Iapetus orbited Saturn just like other moons, it was visible only when it was to the right of the planet, remaining completely invisible when it was to the left. Believe it or not, after a period of great perplexity, Cassini himself hypothesized that one hemisphere of Iapetus must be intrinsically much darker than the other. However, proof was lacking, and for centuries this remained one of the deepest mysteries of observational astronomy. It was only partially resolved by the Voyager probes over 40 years ago, which revealed that Cassini was right. Iapetus' surface is divided into two hemispheres as different as day and night. The two parts actually divide in a pattern similar to the two halves of a tennis ball, embracing each other. Like almost all other moons, Iapetus orbits with the same face always turned towards Saturn. This means that one hemisphere, called the leading hemisphere, always faces the direction of its orbital motion, while the other, called the trailing hemisphere, always faces the opposite direction. Now, the fact that the leading hemisphere is the dark one raises more than a suspicion that the cause of the darkening might be some carbonaceous organic substance that Iapetus encounters along its path. It's a bit like when your car windshield gets covered with dirt and insects. It's just a vague clue for now, but confirmation would come later. Meanwhile, astronomers have tried to explain the cause of this dichotomy with some of the strangest theories. Some suggest that the dark material might come from an internal source, possibly brought to the surface by a combination of meteoritic impacts and volcanism. This theory is supported by the apparent concentration of the material at the bottom of craters, similar to substances found in some meteorites or on comet surfaces. The thickness of the layer is not known for sure. There are no bright craters on the dark hemisphere, so if the dark layer were thin, it would need to be continuously renewed. Otherwise, a meteoritic impact would penetrate beyond the surface layer and reveal the brighter underlying material. An alternative theory suggests that the moon acts like a kind of snowplow in Saturn's system, collecting clouds of dusty debris on the surface of its leading hemisphere as it orbits, which would lower its surface albedo. If you've ever driven your car on the highway through a swarm of insects, these views of Iapetus might bring back some visceral memories. Since only the leading hemisphere, analogous to your car's windshield, collides with the matter directly in front of it, only one side gets covered in insects. Of course, there are no insects in space, but besides Saturn's main rings, there must be something else outside that acts as a source of pollution. And according to most experts, another moon might be responsible for it all. The very distant and tiny moon Phoebe. Phoebe is unusual in several respects. Unlike the other satellites discussed here, it is an irregular moon, meaning it did not form from an early disk of material as the regular Saturnian satellites are believed to have done. Instead, it was initially a freely orbiting member of the Sun's family that became ensnared in Saturn's gravitational net and captured by the giant planet. It is by far the largest of Saturn's irregular moons, and travels around the planet in a retrograde orbit some 8,043,563 miles or 12,869,700 kilometers away, taking 545 days to complete a single revolution. It rotates about its axis every 9.3 hours, is almost spherical in shape, quite heavily cratered, and has a relatively high density of 1.6 times that of water, indicative of a rock and ice composition. The surface of the moon is very dark and is covered by a mixture of water ice, frozen carbon dioxide, phyllosilicates, and organic compounds. There is a possibility that iron-bearing minerals also add to the mix. When the first long-distance space probe images of Phoebe were received, one astronomical writer commented that what was being observed was probably the encrusted nucleus of a giant comet. That seems not to have been too far from the truth, as most astronomers believe that prior to its capture by Saturn, this moon was a centaur or a Kuiper Belt object. The close-up images of this object provided by Cassini may have given us the best likeness of Chiron and its siblings that we are likely to see in the foreseeable future. Phoebe is now known to be associated with a faint ring, which in terms of diameter is the largest in Saturn's ring system. This ring is composed of dark particulate matter, believed to have been ejected from Phoebe's surface by meteoroid impacts. This free-floating material from Phoebe's dark surface helps solve the mystery of the two-faced Iapetus. Like Phoebe itself, the particles thrown up from its surface orbit Saturn in a retrograde direction, gradually spiraling inward toward the planet. As Iapetus follows its direct orbit around Saturn, it sweeps up these particles with its leading hemisphere. However, the full story of Iapetus' dark hemisphere is not just about being covered by Phoebe's debris. The situation is a bit more complex. Being dark, this material absorbs sunlight more readily than lighter-colored materials, converting it into heat and raising the surface temperature of the regions blanketed by Phoebe's detritus. This leads to a thermal runaway process where ice evaporates, exposing darker material underneath, which then absorbs more sunlight, and so on. The result is that ice evaporates from the leading hemisphere and recondenses on the trailing hemisphere, increasing the reflectivity of the latter while darkening the former, creating the extreme contrast in reflectivity and color that we observe today. Apart from the remarkable color difference, there is little to distinguish the leading and trailing hemispheres of this moon. The entire surface appears ancient, heavily pockmarked by impact craters, and devoid of any obvious signs of volcanic activity past or present. The only really odd geological feature is an enormous 12.5-mile or 20-kilometer high equatorial ridge spanning much of the moon's circumference. Along the roughly 800-mile or 1,300-kilometer length over which it can be traced, it remains almost exactly parallel to the equator within a couple of degrees. The presence of this ridge gives the body a strange appearance, often likened to that of a walnut. The ridge contains some of the loftiest mountains in the solar system, reaching over twice the height of Mount Everest. But even this comparison scarcely does justice to the extreme elevation of this feature. The Earth is nearly 8,000 miles in diameter. Iapetus is just 919 miles. Mount Everest is a little under 0.0007 times the Earth's diameter. But the altitude of the Iapetan equatorial ridge is a full 0.014 times the moon's diameter. Proportionally speaking, Everest would need to be around 109 miles high to equal the equatorial ridge. The reason why Iapetus has such a feature is not understood. Some researchers suggest that the ridge might be a remnant of the oblate shape of a rapidly rotating youthful Iapetus. This hypothesis suggests that early in its life, heating by short-lived radioactive isotopes such as aluminum-26 caused this ice rock moon to be in a more plastic state. If it was both plastic and very rapidly rotating, the moon may have deformed into the famous walnut shape before the decay of the heat source and consequent cooling set it into that form. Another hypothesis sees the ridge as due to the upwelling of icy material from beneath the surface, while yet another postulates the collapse of an ancient ring around the moon, depositing material along the equatorial zone. Another variation of this theory suggests that Iapetus once had a moon of its own, a satellite of a satellite, which over time spiraled in towards Iapetus before eventually disrupting and crashing to form the Great Ridge. The ring hypothesis is probably the least likely explanation, as material from a collapsing ring seems inadequate to build a ridge of the required elevation. Evidence of tectonic faulting through the ridge, not commonly seen on Iapetus, suggests that the formation of this feature was more likely driven by internal rather than external forces. But the weirdness doesn't end there. Iapetus has another claim to fame. It has some of the biggest landslides known. Evidence of slides known as long run-out landslides or Sturz storms, some 50 miles or 80 kilometers long, has been found along the crater walls and other slopes of this moon. Their height-length ratio initially puzzled planetary scientists. The landslides of Iapetus sometimes traveled as far as 30 times their height. By comparison, landslides and avalanches on Earth seldom travel more than twice their height. Ice was suspected to play a role in the length of these slides, but experiments with icy mixtures on Earth still failed to match the scale of these events. Somehow the ice on Iapetus acted as though it had a lower friction coefficient than the familiar ice of Earth, allowing ice-rock mixtures on this moon to travel greater distances before stopping. Is there something weird about the ice of Iapetus? Probably not. The most likely hypothesis involves ice melting through friction. Friction between the sliding material and the surface generates heat. If the sliding material is composed of both rock and ice, and if the frictional heat is sufficient, pieces of ice will melt, causing the debris flow to become more fluid and travel further than one composed entirely of solid particles. To complete the scenario, an ancient 400-kilometer wide or 250 miles impact basin appears just above the ridge. The basin is heavily overprinted by more recent, smaller impact craters. The basin rim is delineated by steep scarps that descend to the basin floor. Many of these scarps, as well as the walls of nearby craters, appear bright, probably due to exposed outcrops of relatively clean ice. According to some, this devastating impact may have had something to do with the formation of the long equatorial wall. But this is only speculation, and it will probably be decades before Iapetus decides to reveal its secrets. It will take a dedicated mission, a new discovery, to search for the gateway to the stars on this small moon, just as Arthur Clarke intended. Enceladus, Saturn's icy moon. Facts and history, discovery, and naming. When it comes to moons and planets in space, their discovery is a key part of their history. So who was the one who discovered Enceladus? That would be William Herschel in 1789. But just as impressively, it was during the first use of his new telescope that he got it done. In fact, at the time, the telescope he used was the biggest in the world. The problem, though, was that due to the position of the moon and how it was basically shined over by the brightness of Saturn and its rings, Enceladus was difficult to observe from Earth with smaller telescopes. However, Herschel was in luck, as he found it during a Saturnian equinox, the first moon to be discovered that way. The equinox in question removed some of the glare from the moon so that it could indeed be spotted. Prior to the Voyager missions, the view of Enceladus improved little from the dot first observed by Herschel. We knew general information about the moon, but not much about the nitty-gritty of what made it tick. Thankfully, we were able to get more information later on, obviously. As for its title, the moon is named after the giant known as Enceladus from Greek mythology. But unlike certain other moons, the naming did not stop there. Not one bit. Because unlike other structures, scientists and researchers decided to name various aspects of the moon. Impact craters, for example, were named after characters, whereas other feature types such as fossae, long narrow depressions, dorsa, ridges, planitia, plains, sulci, long parallel grooves, and roops, cliffs, were titled after places. When all was said and done, 85 features on Enceladus had names. That's a lot of things to label. So as you can see, they got a little name happy for this moon. But that just led them to detailing it even more, so it may have just worked out that way for them. Shooting into space. In 2005, something rather special was found out about Enceladus. Specifically, NASA's Cassini spacecraft discovered that icy water particles and gas gushed from the moon's surface at approximately 800 miles per hour. Not something you'd expect from a moon. From a planet, yes, but a moon, not so much. But it wasn't just that it was shooting into space. It was doing so at quite a rate to where it was actually reaching the outer layers of the moon. So much so that it supplies materials to Saturn's E-ring. Only a small fraction of the material ends up in the ring, however, with most of it falling like snow back to the moon's surface, and that's a big reason why the moon is such a bright color of white. A curious thing indeed, filling up a ring with some of the plume, and making the moon bright white with the other. Again, not something you'd expect from a moon. The water jets come from relatively warm fractures in the crust. Several gases including water vapor, carbon dioxide, methane, perhaps little ammonia, and either carbon monoxide or nitrogen gas make up the gaseous envelope of the plume, along with salts and silica. Just as curious to those studying it, the gases are much denser than they first guessed, adding more mystery to everything involved. If you're curious how these plumes really form, that's because there's an ocean in Enceladus that supplies the jets, which is important to note because now scientists are trying to study the E-ring of Saturn in order to study the waters of the moon. Within the ice droplets that make it to the E-ring are peculiar nanograins of silica, which can only be generated where liquid water and rock interact at temperatures above about 200 degrees Fahrenheit, 90 degrees Celsius. What does all that mean? It means that hydrothermal vents might be underneath the moon's surface. If that sounds familiar, it's because we have similar vents on Earth. Ours, though, happen to be on the ocean floor. Enceladus discoveries have changed the direction of planetary science, said Linda Spilker, Cassini project scientist at NASA's Jet Propulsion Laboratory. Multiple discoveries have increased our understanding of Enceladus, including the plume venting from its south pole, hydrocarbons in the plume, a global salty ocean, and hydrothermal vents on the seafloor. They all point to the possibility of a habitable ocean world well beyond Earth's habitable zone. Planetary scientists now have Enceladus to consider as a possible habitat for life, which is a big deal because in the large scale of our solar system, there aren't many places that can be openly considered as possible habitats. That even includes Mars to an extent, because humanity has a lot of work to do to truly make it a viable place to live. But because of the potential ocean in Enceladus, that changes things dramatically, and more thought will be put into the study of this moon. Exploration of Enceladus. Given the overall findings and importance of the moon, it's not surprising that we sent many craft to go and study Enceladus in various ways. The two Voyager spacecraft were the first to get close-up images of Enceladus. Voyager 1 did it in 1980. The pictures received weren't the best, but they revealed a highly reflective surface devoid of impact craters, meaning that the surface might be young in terms of the scale of the solar system. Voyager 2 followed up on that in 1981 and got closer to the moon than the previous attempt, thus we got more clear images, which helped really show what the moon was like. They also revealed a surface with different regions with vastly different surface ages, with a heavily cratered mid to high northern latitude region and a slightly cratered region closer to the equator. These finds also conflict with what other moons of Saturn have, raising various questions yet to be answered, because they couldn't figure out how such diversity could come to the surface of a moon like this and be so different from others. The answers to many remaining mysteries of Enceladus had to wait until the arrival of the Cassini spacecraft in 2004, when it entered orbit around Saturn. Enceladus was considered a priority target by the Cassini mission planners due to past runs with the probes from before. Their results yielded even more information about the moon. These discoveries prompted the adjustment of Cassini's flight plan to allow closer flybys of Enceladus, including an encounter in March 2008 that took it to within just 48 kilometers of the surface. 7 flybys of the moon happened between July 2008 and July 2010. Confirmation of molecular hydrogen, H2, would be an independent line of evidence that hydrothermal activity is taking place in the Enceladus seafloor, increasing its habitability. By contrast, the water thought to be on Jupiter's moon Europa is located under a much thicker layer of ice, which would be problematic to be reached and produce life. Orbits and rotation. Enceladus orbits Saturn every 32.9 hours, fast enough for its motion to be observed over a single night of observation. Very helpful for the scientists wanting to learn more about it. Unlike most of Saturn's larger satellites, Enceladus' rotation always has one face pointed towards Saturn. Unlike Earth's moon, Enceladus does not appear to liberate more than 1.5 degrees about its spin axis. However, analysis of the shape of Enceladus suggests that at some point it was in a 1/4 forced secondary spin orbit libration surface. Voyager 2 was the first spacecraft to observe Enceladus's surface in detail as noted earlier. Because of that, we know that there are 5 different types of terrain on the moon, possibly even more that might have been missed, including several regions of cratered terrain, regions of smooth terrain, and lanes of rigid terrain, often bordering the smooth areas. In addition, extensive linear cracks and scarps were observed. So also as noted, it's a diversity rarely seen before, which makes it all the more exciting to those who want to learn more about it. Given the relative lack of craters on the smooth plains, these regions are probably less than a few 100 million years old. The fresh, clean ice that dominates its surface gives Enceladus the most reflective surface of any body in the solar system, with a visual geometric albedo of 1.38. Because it reflects so much sunlight, its surface only reaches a mean noon temperature of minus 198 degrees Celsius, minus 324 degrees Fahrenheit, somewhat colder than other Saturnian satellites. Yet that makes sense, as we are warm here on Earth because we only partially reflect away the sun's light and warmth, as we don't have a reflective surface as intense as this moon of Saturn. Numerous fractures were found within the older, cratered terrain on Enceladus, suggesting that the surface has been subjected to extensive deformation since the craters were formed. Some areas contain no craters, indicating major resurfacing events in the geologically recent past. There are fissures, plains, corrugated terrain, and other crustal deformations. There are parts of the moon, though, that are a bit odd, such as the bizarre terrain near the South Pole, which wasn't able to get fully imaged by the passing poles. All of this indicates that Enceladus's interior is liquid today, even though it should have been frozen long ago, further suggesting a rather odd history and origin. More on that in a bit. While this may not seem interesting, knowing how the surface of a moon or even a planet is formed and affected by things in space is important in understanding its history. We're still learning things about Mars because of things that keep being found on the surface, shape and size. To be honest, this moon is a rather small satellite composed of ice and rock. It is a scalene ellipsoid in shape, with it being 513 kilometers between the sub- and anti-Saturnian poles, 503 kilometers between the leading and trailing hemispheres, and 497 kilometers between the north and south poles. Enceladus is only 1/7 the diameter of Earth's moon. It ranks 6th in both mass and size among the satellites of Saturn, yet that hasn't stopped it from being viewed as one of the more important moons of Saturn. Paradoxical origin. Aside from its unique surface, there is a bit of a debate as to how Enceladus actually formed, and how it's so different from another moon near it, Mimas. Mimas, the innermost of the round moons of Saturn, is a geologically dead body, even though it should experience stronger tidal forces than Enceladus. This apparent paradox can be explained in part by temperature-dependent properties of water ice. Some predictions state that in regards to Enceladus, there are various temperature states that would work to keep the moon stable, from a low convection temperature to a much higher one, but this is just one phase of the paradox itself. Because Mimas is the other half, and according to models, only a low energy state is expected to be stable, even though unlike its counterpart, it's much closer to Saturn. So the model predicts a low internal temperature state for Mimas, but a possible higher temperature state for Enceladus. So thus you have the paradox, because many aren't sure how Enceladus was able to enter the high energy state that it's currently in. It defies many forms of logic. The significantly higher density of Enceladus relative to Mimas has also been cited as an important factor in resolving the Mimas paradox. It has been suggested that for an icy satellite the size of Mimas or Enceladus to enter an excited state of tidal heating and convection, it would need to enter an orbital resonance before it lost too much of its primordial internal heat. Mimas is of course smaller than Enceladus, and thus would have a much shorter window to cool down, thus adding even more mystery to the paradox. When we'll find out the answer to this mystery is unclear, but many theories have been proposed. Future exploration. As you can see, Enceladus has gotten many researchers and scientists excited about what this moon could mean, not just for the study of the solar system, but also for the growth of humanity in the solar system expansion that is being planned. So thus many more missions are aiming to learn more about it. Such missions include a lander by the German Aerospace Center to study the habitability potential of its subsurface ocean. The European Space Agency, ESA, was assessing concepts in 2008 to send a probe to Enceladus in a mission to be combined with studies of Titan Saturn System Mission, TSSM, though obviously those didn't come to be, mainly because the project was competing for funding with another project. In November 2017, Russian billionaire Yuri Milner expressed interest in funding a low-cost, privately funded mission to Enceladus, which can be launched relatively soon. NASA also had their own mission, but they wanted to send a craft to the moon. Yet it hasn't happened yet. But it's clear that many want to study these waters to see what it could mean for us in the future, because if something incredible is found, it could change even more how we view certain moons in our solar system, as well as seeing whether we might want to try and land people on there in the future. Imagine a moon that looks like a planet-destroying superweapon from a galaxy far, far away, from the Star Wars franchise. That's Mimas, Saturn's Death Star moon. But there's more to this tiny world than its striking resemblance to a fictional space station. Mimas is a fascinating object in our solar system with a violent history and unique features that have captured the imaginations of scientists and Star Wars fans alike. The nickname may seem a bit dramatic, but it is actually quite fitting when you consider the features of Mimas. First of all, let's take a closer look at the moon itself. Mimas is the smallest of Saturn's major moons, measuring only about 400 kilometers in diameter. It orbits around the planet at an average distance of about 115,260 miles. The distance can vary slightly due to Mimas's elliptical orbit, which takes it as close as 113,072 miles and as far as 117,537 miles from Saturn. The exact distance between Mimas and Saturn depends on their positions in their respective orbits at any given time, as well as the gravitational interactions between them and other moons in the Saturnian system. It is a heavily cratered world with many large impact craters visible on its surface. Mimas also has a large mountain at its center, which is about 6 kilometers high and 100 kilometers wide. The mountain is thought to be the result of a geological process that occurred early in Mimas's history. Herschel crater. However, the most striking feature of Mimas is the enormous Herschel crater, which dominates one side of the moon. This crater is over 100 kilometers wide, which is nearly 1/3 of the entire diameter of Mimas. It is also quite deep, with walls that rise up to 5 kilometers above the crater floor. The Herschel crater is what gives Mimas its nickname. The crater has a very similar appearance to the super weapon from Star Wars, with a large circular depression and a smaller protrusion on one side that looks like the weapon's concave dish. In fact, the resemblance is so striking that when the Voyager 1 spacecraft first imaged Mimas in 1980, some of the mission scientists jokingly referred to it as the Death Star moon. Of course, the nickname is not entirely accurate. Mimas is not a superweapon capable of destroying planets, and it is not even capable of sustaining life as we know it. However, the moon is still a fascinating object to study, and the Herschel crater in particular has provided scientists with many insights into the geology and history of the moon. So how did the Herschel crater form? The leading theory is that it was created by a massive impact from a comet or asteroid, which struck Mimas at a high velocity. The impact would have released an enormous amount of energy, equivalent to millions of nuclear bombs, and would have vaporized a large portion of the moon's crust. The resulting shockwave could have caused massive earthquakes and tidal waves, and debris from the impact would have been scattered across the surface of the moon. Over time, the debris settled back onto the surface, forming a ring of material around the newly formed crater. The ring is visible as a series of terraces and ridges which rise up in a series of steps from the crater floor. The steep walls of the Herschel crater also contain many fractures and faults, which are thought to have formed as a result of the impact. The formation of the Herschel crater is a testament to the violent history of our solar system. Impact events like this were common in the early solar system, and they played a major role in shaping the planets and moons that we see today. By studying the impact craters on Mimas and other bodies in our solar system, scientists can learn more about the history of our cosmic neighborhood and the processes that have shaped it over billions of years. Composition of Mimas. But the Herschel crater is not the only interesting feature on Mimas. The moon also has a slightly elongated shape, with its longest axis pointing towards Saturn. This is thought to be the result of tidal forces from the planet, which have caused the moon's shape to become distorted over time. The same tidal forces have also caused Mimas to become tidally locked with Saturn, meaning that the same side of the moon always faces the planet. This is a common phenomenon among moons in our solar system, and it is thought to be the result of gravitational interactions between the moon and its parent planet. In addition to its shape and surface features, Mimas also has a very low density. It has a density of 1.15 grams per cubic centimeter. This density is significantly lower than that of Earth, which has a density of about 5.5 grams per cubic centimeter. The low density of Mimas suggests that it is primarily composed of water ice and a small amount of rock. This is consistent with observations that have shown Mimas to have a heavily cratered surface, which is indicative of a relatively weak, icy crust. The low density also suggests that Mimas does not have a substantial metallic core, as metals are typically much denser than water, ice, and rock. The density of Mimas has important implications for its internal structure and composition, as well as its evolution over time. Understanding the composition and structure of Mimas can help us better understand the formation and evolution of Saturn's moons and the Saturnian system as a whole. The low density also means that Mimas does not have a strong gravitational pull, which makes it difficult for the moon to retain an atmosphere. As a result, the surface of Mimas is exposed to the harsh vacuum of space, with no protection from cosmic radiation and other space weather. Some of the consequences of prolonged exposure to cosmic radiation on Mimas include surface alterations, where cosmic radiation can cause surface alterations on Mimas, including changes in color, texture, and morphology. Over time, this can lead to a heavily cratered surface. Cosmic radiation can also cause temperature changes on the surface of Mimas, which can affect its physical and chemical properties. Another consequence would be the depletion of volatile compounds on the surface of Mimas, including water ice, which is one of the primary components of its composition. And finally, radiation damage to organisms. If any organisms were to exist on Mimas, they would be exposed to high levels of cosmic radiation, which could cause damage to their DNA, leading to mutations and possibly death. These consequences highlight the importance of understanding the effects of cosmic radiation on celestial bodies like Mimas, especially as we continue to explore our solar system. The study of these effects can help us better understand the evolution and history of these bodies, as well as the potential for life to exist in such extreme environments. Missions to Mimas. Despite its harsh environment, Mimas remains an object of interest to scientists and astronomers. The moon has been imaged by several spacecraft, including the Voyager and Cassini missions, which have provided high-resolution images of the surface and revealed new details about the moon's geology and history. In 2005, Cassini made a close flyby of Mimas, providing scientists with high-resolution images of the moon's surface and revealing new details about its geology and history. One of the most significant discoveries made by Cassini was the identification of a large thermal anomaly on Mimas. The anomaly was located near the Herschel crater, which dominates one side of the moon and is thought to have formed as the result of a massive impact from a comet or asteroid. The thermal anomaly was initially thought to be the result of the crater's heating by sunlight, but further analysis revealed that it was caused by a combination of factors, including the moon's internal heat and the reflection of sunlight off the crater's walls. Cassini also provided detailed images of the surface of Mimas, revealing a network of fractures and ridges that suggest the moon has experienced significant tectonic activity in the past. The images also showed evidence of landslides and impact craters, providing scientists with insights into the violent history of the Saturnian system. In addition to its scientific observations, Cassini also captured stunning images of Mimas that revealed its unique appearance and resemblance to the Death Star from Star Wars. These images generated significant public interest and helped to increase awareness of the mission's objectives and discoveries. Scientists continued to study Mimas and other moons in our solar system in order to better understand the formation and evolution of our cosmic neighborhood. Mimas is called the Death Star moon due to its striking resemblance to the planet-destroying superweapon from Star Wars. While the nickname is not entirely accurate, it is a testament to the moon's unique appearance and interesting features. The Herschel crater, which dominates one side of Mimas, is thought to have formed as the result of a massive impact from a comet or asteroid, and provides scientists with insights into the violent history of our solar system. Mimas is also notable for its low density, elongated shape, and lack of a substantial atmosphere. Despite its harsh environment, the moon remains an object of study for scientists and a fascinating target for exploration. Studying Mimas can provide us with insights into the geology and history of our solar system, as well as a better understanding of how celestial bodies like this one evolve and interact with each other over time. Whether you're a Star Wars fan or a scientist, Mimas is an intriguing object to explore, and its story is sure to captivate us for years to come. Hyperion is the mysterious moon of Saturn. located in the outer reaches of our solar system. People have been wondering why it is shaped like it is and whether there is life on Hyperion for centuries, but no one knows for sure. Do you? It is a great mystery that continues to fascinate scientists, adventurers, and daydreamers like you. In the past few years, more knowledge has been discovered about this mysterious moon. A spacecraft named Cassini was sent to explore Saturn and its moons and reached Hyperion in the year 2004. Astronomers have been studying photographs taken by Cassini and have made some interesting observations. They have noticed that Hyperion has a strange hexagonal shape and is covered in craters. Additionally, they have observed that there is a very icy surface on Hyperion, making it look like a snow globe from far away. What secrets are hidden away on this distant object? Hyperion has a comparatively small radius of 135 kilometers, making it 1/12 the size of Earth's moon and 1/400th of Saturn. It orbits around Saturn at a distance of 1,500,000 kilometers and takes 21 days to complete an orbital period. Hyperion has many deep craters that give it a spongy outward appearance. The biggest crater on Hyperion has a diameter of 121.57 kilometers and is over 9.6 kilometers deep. On average, its surface temperature is minus 180 degrees Celsius. Hyperion, whose shape resembles that of a potato, is the biggest known irregularly shaped moon in the solar system, with dimensions of 410 by 260 by 220 kilometers. It is possible that it used to be a larger, more spherical satellite, which was hit by a major collision in its early history. As a result of this impact, nearby pieces of rocks and dust clumped together and formed Hyperion. The complex dance of Saturn's 62 moons is a mesmerizing illustration of the beauty of the laws that govern our universe. This complex conglomeration of gravitational resonances hurls the moons around their planet, shaping Saturn's rings and heating some of them, possibly to the point of sustaining life beneath their surfaces. One of the standouts is Hyperion, or Saturn VII, which takes center stage among the moons. How did Hyperion get discovered? The unusual lunar body was initially found in 1848 by three separate teams of astronomers, William and George Bond, as well as William Lassell. The two Bonds made their observation just 2 days prior to Lassell's. All who contributed to its discovery were acknowledged. John Herschel, the renowned English polymath and astronomer, proposed a creative idea of naming the moons of Saturn after the siblings of Kronos, the Greek counterpart of the Roman god Saturn, from mythology. The name Hyperion is inspired by Greek mythology and comes from the name of the god Hyperion. He was the offspring of Uranus and Gaia and the brother of Kronos. He was the husband of Thea and the father of Helios, sun, Eos, dawn, and Selene, moon. Shape of Hyperion. Astronomers hypothesize that Hyperion, which has a weird-looking shape unlike the other spherical moons, is likely a remnant of a larger moon that was hit by a massive object. This impact caused the dust from the collision to be drawn together through gravity, resulting in the formation of Hyperion. We know moons that are usually spherical, so why is Hyperion so weirdly shaped, almost like a potato? The irregular shape of Hyperion, the largest known non-spherical moon in the solar system, is likely due to the combination of smaller rock fragments that lack the mass to form into a sphere with enough gravitational pull for a single structure. Instead, the collection of individual rocks created an irregular shape. Due to its irregular shape, this object can rotate around 3 axes with an unpredictable and ever-altering motion. It is impossible to predict the path of the object's rotation or the exact moment when it will pause or change direction. The irregular shape creates a sort of chaotic motion that is captivating and mesmerizing to watch. It is almost like watching a kaleidoscope or a top, with the object gracefully dancing and twirling in unpredictable motions. Hyperion's orbit around Saturn is non-circular, meaning it is elliptical and highly influenced by Triton, the planet's largest moon. The gravitational pull between them causes the two to speed up and slow down based on the changing distance between them. As it is far from Saturn and in close resonance with Triton,
Hyperion does not remain facing the planet, instead rotating roughly over 13 days in its 21-day orbit. If Hyperion looks so much like a sponge, does that mean it is spongy? Despite having the same texture as your shower sponge loofah, Hyperion is not a sponge. It's less dense than water, being only slightly over half as dense. It is said that frozen methane or carbon dioxide could be the cause of its porous look. The majority of it is made up of large amounts of water ice and a slight amount of solid rock, although the exact composition is still unknown. Hyperion's surface is heavily cratered, giving it a sponge-like appearance due to the deep indentations left by impacts on its icy surface. These craters lack the molten material seen on other moons such as Phoebe and Iapetus. As Hyperion is located far from Saturn, it is exposed to a greater probability of collision with space debris. If you happen to go on a space vacation in the near future, I advise bringing your own loofah instead of relying on the Hyperion sponge. Under the surface of Hyperion. Now that we know what the surface of Hyperion is like, let's dig deeper and find out what's going on under it. When the Cassini spacecraft flew close to Hyperion in September of 2005, it revealed astonishing discoveries. Carbon dioxide, water ice, and dark material with a spectral profile akin to hydrocarbons were all detected. Scientists were amazed to discover that the same combination of carbon and hydrogen atoms found in meteorites, comets, and space dust in our galaxy were also present on the moon's surface. These molecules, when frozen in ice and exposed to ultraviolet radiation from the sun, can undergo reactions to form new molecules of great biological importance. The presence of carbon compounds in Hyperion, as well as the fact that the moon is much darker than most moons in our solar system, has made Hyperion an intriguing target for astrobiological investigations. Scientists are now looking into the possibility that conditions on the surface of Hyperion could be conducive to the formation of simple organic molecules, conditions that are vital to the development of life. If organic molecules were indeed found on Hyperion, this would provide further evidence for the possibility of life existing in our solar system and beyond. Life on Hyperion. This poses the usual big question: does life exist on Hyperion? At the moment, it is unrealistic to assert that Hyperion is habitable for organisms solely based on the fact that basic chemistry is present, as indicated by the presence of biomolecules. Although this possibility cannot be denied, further evidence is needed to make a conclusive determination. Various factors must be taken into account in further research of Hyperion's potential habitability. For example, the presence of an atmosphere and other necessary conditions, such as the right temperature and pressure range, must be considered. In addition, the availability of resources such as water and energy should also be investigated. Additionally, the potential impact of the radiation environment of the moon must be accounted for in order to determine if this environment is too harsh for life to exist in any form on Hyperion. Once these factors have been investigated and assessed, further research can be conducted to determine if Hyperion could support a form of life that is adapted to the environmental conditions present. By studying biomarkers, researchers may be able to determine whether any form of life is present or has ever been present on Hyperion. If the prerequisites for sustaining life are found and the biomarkers are positive, it would be possible to make a definitive statement about the habitability of Hyperion. Although the lack of oxygen rules out the possibility of life forms that need it to breathe, the universe is vast and anything could be possible. Exploring beyond Earth has revealed that there are many unique and strange planets, moons, and other celestial bodies scattered throughout the universe. Some of them may even contain environments that are capable of sustaining non-oxygen dependent life forms, such as extremophiles, who can live in extreme temperatures and lack of oxygen. The sheer size and age of our universe means that it is impossible to know what forms of life may exist in the depths of space. Who knows? Perhaps even now there are alien civilizations living on faraway planets, just waiting to be discovered. For now, the questions remain unanswered, and more exploration is needed to reveal the true mystery of Hyperion. What we do know is that the icy moon is incredibly unique. with its irregular shape and spongy cratered surface. And through further research, we can gain a better understanding of the laws that govern our universe and explore the possibilities of life existing on other moons. Until then, Hyperion will remain a captivating mystery, beckoning us to unravel its secrets and discover what may lie beneath. Miranda, the Frankenstein moon orbiting Uranus. Sure, it's a matter of taste, but many agree that one of the strangest moons in the solar system is the misshapen Miranda, the smallest and innermost of Uranus's 5 major moons. Discovered by Gerard Kuiper on February 16, 1948, it was named after a heroine from Shakespeare's The Tempest. However, the Shakespearean Miranda is a young and beautiful woman, while this moon looks like it was pieced together, much like Frankenstein's monster. This small, lumpy moon features a surface covered with skewed and interesting ice slabs, oddly rugged terrains, pockmarked plains, and dark, irregular canyons. How did this deformed landscape come to be? Was the moon bombarded by meteors? Did it survive a massive collision? Is it the result of stretching and squeezing caused by Uranus's gravity? We don't know yet. Or maybe we do. Follow along and let's try to uncover the truth together. The renowned astronomer Gerard Kuiper identified the elusive Miranda in a photograph taken with the 2-meter telescope at the McDonald Observatory in West Texas, which was the second largest in the world at the time, after the 2.5-meter Mount Wilson telescope. It had been over 100 years since the last discovery of one of Uranus's moons. The first two, and the largest, Oberon and Titania, were found in 1787 by William Herschel, the same astronomer who discovered Uranus in 1781, then the 7th planet in the solar system. In 1851, William Lassell discovered Umbriel and Ariel. Each of Uranus's moons is named after a character from Shakespeare, and Miranda, for whom the moon is named, is the protagonist of The Tempest, the obedient and virtuous daughter of Prospero, who was exiled with only her father from the age of 3, never interacting with other humans until her teenage years. Fittingly, the moon's name is a good metaphor for the moon itself. Like Shakespeare's Miranda, who spends most of her youth obediently in her father's shadow, Uranus's Miranda is the closest of the planet's moons. And like all the others, it always shows the same face to the planet. To give you an idea of Miranda's environment, Uranus has 5 major moons, whose mass is sufficient for their gravity to shape them into spheroids. The 4 largest moons are Ariel, Umbriel, Oberon, and Titania, with diameters ranging from 1,200 to 1,600 kilometers, 745 to 1,000 miles, less than half the size of our moon, while the smallest of the large moons is Miranda, with a diameter of 470 kilometers or 292 miles. The moons have similar compositions, consisting of a rocky core and an icy mantle with rather dark surfaces. Miranda is an exception, appearing to be mostly ice without a differentiated core and having a brighter surface. The 2 largest moons, Oberon and Titania, might have a layer of liquid water between the core and the mantle. The moons seem to have formed together with the planet or shortly thereafter, sharing Uranus's bizarre axial tilt, indicating a common formation. In addition to the so-called classical moons, Uranus has other smaller, irregularly shaped satellites divided into 2 groups. The first group consists of 13 moons that orbit closer to the planet than Miranda, with diameters ranging from about 15 to 150 kilometers, 9.3 to 93 miles, closely linked to the formation and maintenance of the ring system. The second group consists of 9 more distant moons that move in retrograde orbits compared to the previous ones, with diameters ranging from 10 to 190 kilometers, 6.2 to 118 miles, likely Kuiper Belt objects captured long ago by Uranus's gravity. Miranda's surface appears to be composed of water ice mixed with silicate and carbonate compounds with traces of ammonia. Like the other moons of Uranus, its orbit lies in a plane perpendicular to the planet's orbit around the Sun, and like the planet, it is subject to extreme seasonal variations. Like Uranus's other 4 major moons,
Miranda likely formed from an accretion disk that surrounded the planet shortly after its formation, or after the catastrophic event that caused its unusual tilt. However, Miranda is tilted 4.3 degrees relative to Uranus's equatorial plane, the most pronounced tilt among Uranus's major moons. This, as we'll see shortly, might have had some consequences. We mentioned Miranda's discovery in 1948. Well, it would take 38 years before that faint dot of light photographed by Kuiper could become a world to explore. And the credit for revealing the true face of that world didn't go to new generations of telescopes, but to one of the first interplanetary probes. It was Voyager 2 during its flyby of the planet in 1986 that had the opportunity to study Miranda more closely than any other moon of Uranus. And here's a curious fact. The first and only spacecraft to ever visit Uranus chose the worst possible time to do so. Think about it. On January 24, 1986, Voyager 2 passed through the satellite system of the seventh planet in the solar system, and just 4 days later, the tragic Challenger shuttle explosion occurred at launch. Suddenly, as you can imagine, distant Uranus and its moons didn't seem so important to the public anymore, and the amazing discoveries made by the probe were overshadowed for a long time. Did I say amazing? Well, yes, the adjective is strong, but not exaggerated. During its brief and fast flyby, Voyager discovered 11 more small moons and confirmed the existence of the rings. Not only that, passing just 29,000 kilometers or 19,000 miles from Miranda's surface, the probe managed to take several photographs of the small moon. This wasn't an easy task because the cameras had to rotate automatically with precision during each long exposure to the faint sunlight to compensate for the spacecraft's rapid speed. Otherwise, the images would have been blurred. Yet, when the photos were shown at NASA's Jet Propulsion Laboratory, jaws dropped. The images were all perfect, but Miranda's surface was like nothing anyone had ever expected. Voyager's photographs revealed that Miranda's surface is a bizarre patchwork of winding valleys, parallel grooves, fault scarps, and cratered plateaus. These topographical features were a surprise because the moon was thought to be too small, being only a third the diameter of its much less topographically diverse siblings, Titania and Oberon, to have experienced the extensive tectonic activity needed to shape such varied terrain. That world looked like a sample of geological oddities, as if some omnipotent being had used scissors and glue to combine features from different places. Absolutely random. Huge canyons across its surface apparently created by tectonic faults. Some of these are 19 kilometers deep or 11.8 miles, dwarfing our planet's Grand Canyon, which measures about 1.6 kilometers or 1 mile at its deepest point. Traced regions connect younger surfaces with seemingly older ones in a mix that makes no sense, appearing to be built from the inside out. It's as if at one time, lighter density materials emerged from below instead of flowing from above. But what about that tectonic behavior? How does such a small body acquire that kind of internal heat? Experts say that nearby Uranus must have heated the small moon through tidal forces, and that the plastic material somehow found a way to ooze out, creating a carnival of disparate features. How this small moon became so is still a mystery. One theory suggests that shortly after its formation, Miranda was just a smooth ball of ice, but then it was repeatedly destroyed by collisions during the period over 4 billion years ago, when solar system bombardments were the norm. Researchers think Miranda might have been completely destroyed and then totally reformed, using blocks of various sizes from its previous incarnation 4 or 5 times during its tumultuous history, until one or more impacts shattered it. Eventually, the pieces would have come back together, but not in a way that made much sense. An almost acceptable scenario if it weren't for some of Miranda's surface features that defy any explanation. And I'm referring to the structures known as coronae, absolutely unique in our solar system. These coronae, essentially polygonal regions that differ significantly in appearance and color from the surrounding areas, are visible in Miranda's southern hemisphere, each extending at least 200 kilometers or 124 miles in diameter. The largest, ardent corona, features parallel ridges and troughs, resembling a ski slope, that reach up to 2 kilometers or 1.2 miles in elevation. Elsinore, the second corona, has an outer belt about 80 kilometers wide or 50 miles, relatively smooth and rising about 100 meters from the surrounding terrain. Finally, Inverness has a rectangular shape with a large, bright V figure in the center. It's worth noting that Voyager's quick flyby didn't allow for photographing Miranda's northern hemisphere, which was in complete darkness, so we can't know if coronae are present all over the surface. There are other hypotheses about their origin, of course, but the data is still too scarce to favor one in particular. The oldest and most immediate suggests that the coronae are sites of large impacts from rocky or metallic meteors that partially melted the icy subsurface and caused episodic periods of muddy water rising to Miranda's surface and then refreezing. Another theory proposes that these regions are simply the outcropping points of ancient hotspots in the 160 kilometers or 100 miles thick crust. The evidence of volcanism and tectonic phenomena within the coronae suggests they formed over hot plumes rising from Miranda's core, expanding as they approached the surface, fracturing the crust and triggering local volcanism. There's a problem though. Miranda is currently an incredibly cold moon, but the upwelling of material from the depths can only happen with some form of heat and tectonic activity. It's true that in recent decades, scientists have identified volcanoes on Jupiter's moon Io, ice geysers on Saturn's moon Enceladus, lakes on Titan, plate tectonics on Europa, and more. But to have all this, you need some source of heat, and there doesn't seem to be one for Miranda, which is frozen at about minus 212 degrees Celsius or minus 350 degrees Fahrenheit. After much thought, planetary scientists have found a loophole. You might remember that we mentioned Miranda's unexpected orbital tilt, about 10 times greater than that of the planet's other major moons. Well, this could have happened if its orbit was originally much more eccentric than it is now. This would have led to close encounters with other moons, which could have increased its tilt. And if Miranda's orbit was indeed stretched, it would have greatly increased the difference between the moon's maximum and minimum distance from Uranus. Thus, Uranus's gravitational pull would have been sometimes stronger, sometimes weaker, causing Miranda to compress and relax repeatedly, just like a stress ball squeezed in your hand. This would have heated it up, and the heat would have melted and pushed the ice upwards in a process physicists call convection. Each periodic upwelling of ice would have tried to spread out as it reached the surface, crumpling into the ridges and valleys that characterize the coronae. The fact that these regions are relatively crater-free fits perfectly with this scenario. The coronae can't be much more than a few 100 million years old, peanuts compared to the rest of the surface, which dates back billions of years, consistent with the idea that Miranda probably acquired a circular orbit and lost its heat generation around the same time. Everything fits, but since it is based on a handful of images taken almost 40 years ago, it might be difficult to prove definitively. Another mission is needed, but there doesn't seem to be much on the horizon immediately. One proposal from NASA to visit Uranus and its moons is Oceanus, which would launch around 2030 and arrive in the Uranian system in 2041. On the other hand, ESA has proposed Odinus, which would launch in 2034 and arrive 9 years later. There's also MUSE, Mission to Uranus for Science and Exploration, which would launch in 2026 and arrive near Uranus in 2044. But it's all still on paper. Both NASA and ESA agree that future missions should include an orbiter that could study the Uranian system and its moons for a long time, yielding results that would be far more significant than those of missions involving only a close flyby, like Voyager 2. Ariel, Uranus's brightest moon. The discovery of Ariel. In terms of its finding, Ariel was discovered on October 24, 1851 by William Lassell. It is named for a sky spirit in an Alexander Pope story and Shakespeare's The Tempest. which is not too uncommon given the power that literature and mythology have in regards to naming things like this. Both Ariel and the slightly larger Uranian satellite Umbriel were discovered by William Lassell on the same day, believe it or not. Although William Herschel, who discovered Uranus's two largest moons, Titania and Oberon, in 1787, claimed to have observed 4 additional moons. This was never confirmed, and those 4 objects are now thought to be spurious. If you look at the history of finding planets and moons, you'll find similar stories of astronomers trying to get credit because of believed discoveries. All of Uranus's moons are named after characters from the works of William Shakespeare or Alexander Pope. The names of all 4 satellites of Uranus, then known, were suggested by John Herschel in 1852 at the request of Lassell. Ariel is named after the leading sylph in one of Pope's stories. It is also the name of the spirit who serves Prospero in Shakespeare's The Tempest. The moon is also designated Uranus I, which is a more generalized title to help show which moons were discovered in what order and is a common thing across multiple moons of various planets. Its surface. All of Uranus's larger moons, including Ariel, are thought to consist mostly of roughly equal amounts of water, ice, and silicate rock. Carbon dioxide has also been detected on Ariel, which is important in helping determine various things about the moon itself. Ariel's surface appears to be the youngest of all the moons of Uranus. That is believed because it has few large craters and many small ones, indicating that fairly recent low-impact collisions wiped out the large craters that would have been left by much earlier, bigger strikes. You might think, but why does that matter? Scientists like to use impact craters to help determine certain things about the surface, as well as indications of where to look for materials of asteroids or meteors that might have pelted the surface of certain moons or planets, because getting samples of them can help tell a timeline for various things, including the history of the planet. Ariel is also thought to have the most recent geologic activity of Uranus's larger moons. It is transected by grabens, which are fault-bounded valleys. Ariel has the brightest surface of the 5 largest Uranian moons, but none of them reflect more than about a third of the sunlight that strikes them. This suggests that their surfaces have been darkened by a carbonaceous material. Ariel's brightness increases dramatically when it is in opposition. That is, when the observer is directly between it and the sun. This indicates that its surface is porous, casting reflectivity, decreasing shadows when illuminated at other angles. This is another curious thing that scientists like to study, as it can help determine how the moon came to be and the events that led to its current form. Rotations and orbits. Among Uranus's 5 major moons, Ariel is the second closest to the planet, orbiting at a distance of about 190,000 kilometers or over 118,000 miles. Its orbit has a small eccentricity and is inclined very little relative to the equator of Uranus. Its orbital period is around 2.5 Earth days, coincident with its rotational period. This means that one side of the moon always faces the planet, a condition known as tidal lock, which is a key thing in regards to temperature. More on that later. Ariel's orbit lies completely inside the Uranian magnetosphere. The trailing hemispheres, those facing away from their directions of orbit, of airless satellites orbiting inside a magnetosphere like Ariel are struck by magnetosphere plasma, co-rotating with the planet. This bombardment may lead to the darkening of the trailing hemispheres observed for all Uranian moons except Oberon. Ariel also captures magnetospheric charged particles, producing a pronounced dip in energetic particle count near the moon's orbit observed by Voyager 2 in 1986. Observation and exploration. The only close-up images of Ariel were obtained by the Voyager 2 probe, one of the most important scientific tools in the history of the space program, which photographed the moon during its flyby of Uranus in January of 1986. The closest approach of Voyager 2 to Ariel was 127,000 kilometers, 79,000 miles, significantly less than the distances to all other Uranian moons except Miranda. The best images of Ariel have a spatial resolution of about 2 kilometers. They cover about 40% of the surface, but only 35% was photographed with the quality required for geological mapping and crater counting. meaning that there is a lot more to learn from the surface of the moon. At the time of the flyby, the southern hemisphere of Ariel, like those of the other moons, was pointed towards the sun, so the northern, dark hemisphere could not be studied. No other spacecraft has ever visited the Uranian system. The possibility of sending the Cassini spacecraft to Uranus was evaluated during its mission extension planning phase. It would have taken about 20 years to get to the Uranian system after departing Saturn, and these plans were scrapped in favor of remaining at Saturn and eventually destroying the spacecraft in Saturn's atmosphere. What this means on the whole is that there could be a chance to go and try to do a closer flyby for the moon should the opportunity arise, especially with the desire to further go and explore our solar system growing with every year as we potentially get closer to sending a craft to Mars and other potentially viable spots in the solar system. If done correctly, it might not just go and help explore Ariel, but also explore the other moons of Uranus. But whether this actually happens is up for debate. Atmosphere. Despite there being carbon dioxide on the moon of Ariel in some capacity, there is no detectable atmosphere or magnetosphere that we can find. While this may be on the surface sound like an okay thing, it's honestly not. Because when you want to look for a place to live in the universe, an atmosphere is preferable for a variety of reasons. Without it and the magnetic field, that means that not only will anything on the surface be open to getting hit by various cosmic rays, it makes it all the more likely that asteroids and meteors will bombard the place. Which, if you recall, is something we know happens on Ariel, especially with the smaller space rocks. Now, to be clear, this doesn't make it the most uninhabitable place ever, but it is a major deterrent in terms of explorations and wanting to go there for one reason or another to colonize. Surface temperature. Measurements have shown that Ariel's surface temperature rises and falls quickly with the coming and going of sunlight, without a thermal inertial lag. That supports the picture of a porous surface, which would tend to insulate the moon and keep the subsurface from heating up. This texture could be the result of eons of micrometeorite strikes tilling the soil. In an earlier time, Ariel appears to have undergone enough heating to allow differentiation, a separation in which heavier materials sink towards the core and lighter material floats at or near the surface. Models indicate that tidal interactions with Uranus may provide an important source of heat. But whether that heat is enough to do certain things, including live on the surface by channeling that heat, is up for debate. But given how the moon is in tidal lock and that the temperatures rise and fall, it's unlikely. Seasons. Because Ariel, like Uranus, orbits the sun almost on its side relative to its rotation, its northern and southern hemispheres face either directly towards or directly away from the sun at the solstices. This means it is subject to an extreme seasonal cycle, just as Earth's poles see permanent night or daylight around the solstices. So Ariel's poles see permanent night or daylight for half a Uranian year, 42 Earth years, with the sun rising close to the zenith over one of the poles at each solstice. The Voyager 2 flyby coincided with the 1986 southern summer solstice, when nearly the entire northern hemisphere was dark. Once every 42 years, when Uranus has an equinox and its equatorial plane intersects the Earth, mutual occultations of Uranus's moons become possible. A number of such events occurred in 2007-2008, including an occultation of Ariel by Umbriel on August 19, 2007. Composition. Ariel is the fourth largest of the Uranian moons and may have the third greatest mass. Its density indicates that it consists of roughly equal parts water ice and a dense non-ice component, which could consist of rock and carbonaceous material, including heavy organic compounds known as tholins. The presence of water ice is supported by infrared spectroscopic observations, which have revealed crystalline water ice on the surface of the moon, which is porous and thus transmits little solar heat to layers below. Water ice absorption bands are stronger on Ariel's leading hemisphere than on its trailing hemisphere. The cause of this asymmetry is not known, but it may be related to bombardment by charged particles from Uranus's magnetosphere. The energetic particles tend to sputter water ice, decompose methane trapped in ice as clathrate hydrate, and darken other organics, leaving a dark carbon-rich residue behind. Except for water, the only other compound identified on the surface of Ariel by infrared spectroscopy is carbon dioxide, CO2, which is concentrated mainly on its trailing hemisphere. Ariel shows the strongest spectroscopic evidence for CO2 of any Uranian satellite, and was the first Uranian satellite on which this compound was discovered. The origin of the carbon dioxide is not completely clear, and as we noted, there is no atmosphere to contain it or make sure it's near the surface. It might be produced locally from carbonates or organic materials under the influence of the energetic charged particles coming from Uranus's magnetosphere or solar ultraviolet radiation. This hypothesis would explain the asymmetry in its distribution, as the trailing hemisphere is subject to a more intense magnetosphere influence than the leading hemisphere. Another possible source is the outgassing of primordial CO2 trapped by water ice in Ariel's interior. The escape of CO2 from the interior may be related to past geological activity on this moon. Origins of Ariel. As with all bodies in the sky, many wondered how the moons of certain planets formed. Ariel is thought to have formed from an accretion disk or subnebula, a disk of gas and dust that either existed around Uranus for some time after its formation or was created by the giant impact that most likely gave Uranus its large obliquity. Significant amounts of carbon and nitrogen may have been present in the form of carbon monoxide, CO, and molecular nitrogen, N2, instead of methane and ammonia. The moons that formed in such a subnebula would contain less water ice, with CO and N2 trapped as clathrate, and more rock explaining the higher density. The accretion process probably lasted for several thousand years before the moon was fully formed, and ever since its forming there have been rocks pelting the surface, including canyons that may have been around for about 200 million years. Will we go to Ariel? As noted previously, there is a large desire to go and try to make our presence felt throughout the solar system, and there are certain moons out there that might just serve our needs. However, whether Ariel is one of them is up for debate. Without an atmosphere, there are immediate problems involving gas and protection. The tidally locked rotation doesn't help either. Add to that, while there has been water detected on the moon, it's unclear if it's reachable in certain areas or will be able to be processed into drinkable amounts. Not to mention, Uranus is the 7th planet in the solar system, and at present it would take many years to get from Earth to it in a probe, let alone a colony vessel. It's not out of the question, but it is definitely a place that is on the back burner right now, if you will. Triton, the alien planet that became a moon. Triton is the largest moon in the Neptune system and among the largest in the solar system. It was found on the night of October 10, 1846 by English astronomer William Lassell, just 17 days after the discovery of the planet it revolves around. Strangely and contrary to his habits, Lassell gave it no name. The one proposed in 1880 by Camille Flammarion, who named it Triton after the son of the god Neptune, remained in informal use even until 1949, when the astronomical community decided to finally make it official. A strange moon from the beginning, then a name that inspires vision of dark, icy landscapes at the edge of the solar system. One of the most alien and mysterious of known worlds. What do you say? Shall we try to explore it further? Voyager 2 spacecraft swept silently over the royal blue clouds of Neptune at the ragged edge of our solar system and revealed a world unlike any other. A world of wild weather, a reservoir of energy, and a place quite unlike its near twin, Uranus. The tiny spacecraft's observations of Neptune turned up many more questions than answers, as it would close passage by one of the solar system's strangest moons, Triton. After passing over Neptune's north pole, Voyager 2 headed southwards, hurtling through the giant planet's ring plane toward Triton, which had grown steadily larger over the preceding 15 months. By August 25, 1989, the moon covered more than half of the spacecraft's narrow-angle lens. But despite its size, it soon became apparent that Triton was far smaller than anticipated, only 2,700 kilometers in diameter. Pre-Voyager dimension estimates based upon the amount of sunlight Triton reflected had yielded erroneous results. In fact, at that time it was speculated that Triton's diameter was even more than 5,000 kilometers,
vying with Ganymede and Titan for the title of largest moon in the solar system. Image motion compensation techniques trialed at Uranus came into their own and held the spacecraft sufficiently steady to acquire some of the most astonishing map-quality photographs of the entire mission. Moving at 63,730 kilometers per hour, Voyager 2 passed within 39,800 kilometers of Triton's center, revealing a world of profound complexity and a spectacular conclusion to a 12-year, 4-planet grand tour. In the following years, the discovery of Eris and the great media overlap associated with the downgrading of Pluto stole the show from this distant and mysterious satellite. Yet its peculiarities are truly extraordinary, both from a dynamic and physical point of view. At first glance, Triton seems to have all the makings of a natural child of the Neptune satellite system. Indeed, it always turns the same face to the gas giant, like the Moon to Earth and Galilean moons to Jupiter, and its orbit is almost perfectly circular. Two features that usually stand for the fact that a satellite was formed at the same time as the planet to which it belongs. It would therefore seem impossible to see Triton an intruder. Yet there is some oddity in its orbit that, if detected, would immediately make us realize that Triton could not have been born there among the other satellites of Neptune. An anomaly that, considering also the important size of the object, cannot but provoke disbelief. What are we talking about? Well, the fact that Triton's orbit is retrograde. Basically, Triton is like a big truck going the wrong way on the highway. A very strange thing indeed, because all larger objects, since they formed from the same rotating dust disk, orbit the Sun counterclockwise. Mind you, there are other moons in the solar system that revolve around their planet in a retrograde direction, but these are tiny moons, basically small asteroids captured by planets in a variety of ways, and all located on the periphery of the satellite system that received them. Triton, on the other hand, is very close to Neptune, only 350,000 kilometers, less the distance between the Moon and the Earth. Moons in retrograde orbits cannot form in the same region of the solar nebula as the planets they orbit, so Triton must have been captured from elsewhere. It might therefore have originated in the Kuiper Belt, the ring of small icy objects extending beyond the orbit of Neptune. Thought to be the point of origin for the majority of short-period comets observed from Earth, the belt is also home to several large planet-like bodies, including Pluto and Eris. Triton is only slightly larger than Pluto and nearly identical in composition, which has led to the hypothesis that the two share a common origin. The most recent and widely accepted hypothesis suggests that before its capture, Triton had a mass companion similar to Pluto's satellite Charon, with which it formed a binary system. When the two bodies, probably orbiting on their own in the Kuiper Belt along a very eccentric orbit, got too close to Neptune, Triton transferred all its orbital energy to its companion, who was ejected from the system, while Triton was captured and forced to follow a retrograde orbit. This catastrophic encounter would also lead to the almost complete destruction of Neptune's satellite system. In fact, the sizes of the other 13 moons, very small objects, offer persuasive evidence that some catastrophic sequence of events may have occurred in Neptune's distant past. Unlike the other three gas giants, the planet does not have, in fact, a system of mid-sized moons with diameters ranging from roughly 500 to 1,500 kilometers. Some astronomers have suggested that the planet did once possess a family of mid-sized moons, but that the arrival of Triton either scattered them, destroyed them, or ejected them from the Neptunian system altogether. The fact of the retrograde orbit is undoubtedly the oddity that more than the others makes Triton a dark and almost magical world worthy of a fantasy novel. But what can we say about its surface? Here Triton records another record. It is in fact the coldest body among those studied in the solar system, with a surface temperature of minus 230 degrees Celsius, colder than even Pluto. Its low temperature and non-negligible mass allows it to hold a tenuous atmosphere, composed of 99% molecular nitrogen and the rest of methane and carbon monoxide. The surface pressure is less than 1/70,000th of Earth's. At that temperature and distance from the Sun, one would expect an ice ball marked by numerous impact craters, a monotonous landscape frozen in time. But no, Triton's surface is constantly renewing itself. Voyager 2's highest resolution images covered only a third of Triton's surface and revealed a curious, ubiquitous greenish terrain, which was nicknamed cantaloupe, due to its textural similarity to the rigid skin of a cantaloupe melon.
Visually, this took the appearance of a series of roughly circular, interlocking depressions, each about 25 kilometers across. The cantaloupe terrain is crisscrossed by long, interconnected ridges, which are thought to have been caused by one or more epochs of melting and near-complete resurfacing of Triton. Speculations continue to abound that the heat source for this melting comes most likely from the tremendous heat associated with the moon's capture by Neptune and the subsequent circularization of its orbit. These immense tidal forces are to be responsible for substantial crustal fractures and for the melting of the moon's surface, which left large, smooth regions or filled basins and craters with lava-like flows, probably of water ice. The largest of its few visible craters, named Mazomba, measures only 27 kilometers in diameter, indicating the relative youth of its present surface. Spectroscopic investigations revealed the presence of ice of 5 different species in the soil: water, methane, carbon dioxide, nitrogen, and carbon monoxide. More than half of the moon is covered with a solid solution of nitrogen, with traces of methane and carbon monoxide. Water ice is probably the main component of the mantle and crust, although pools of water and frozen carbon dioxide are present on the rest of the surface studied by Voyager. Most of the features seen by Voyager 2 are believed to be solid water ice, which is frozen so hard that it has the consistency of rock at these frigid temperatures. It has been argued that liquid might still be emerging cryovolcanically from the depths of Triton, freezing onto the surface and obliterating all but the very youngest craters. Volcanism had previously been seen only on Earth and on Jupiter's moon Io, but in August 1989, icy plumes of geysers and their after effects were clearly detected on Triton. Indeed, during the flyover, Voyager 2 managed to photograph at least 4 active geysers, which were characterized by vertical columns of black smoke rising up to 8 kilometers in altitude, and then bending parallel to the surface, driven by the prevailing winds over 100 kilometers away. This phenomenon could explain the 100 or so dark streaks formed by the deposition of fine dust that were photographed by Voyager. For some, Triton's geysers would result from a kind of greenhouse effect at work in the ice surface exposed to the sun's rays. Frozen nitrogen is in fact very transparent, allowing light to penetrate it for several meters. It is enough for the deeper ice to be warmed by a couple of degrees for it to sublimate, generating the pressure necessary to erupt to the surface and to project into the tenuous atmosphere a column of nitrogen crystals and dark dust consisting of organic or rocky material. No connection with endogenous activity such as that active on Europa. Then, but to many other planetologists, the presence of geysers instead immediately suggested that Triton too might harbor a large ocean of liquid water under its icy crust formed by the heat of tidal friction. Tidal friction, however, is not the only source of heat within an Earth body. There is also radiogenic heating. This is the heat produced by the decay of radioactive isotopes within a moon or planet, and this process can create heat over billions of years. But doesn't heat plus water equal life? Well, the probability that life forms could develop in the depths of Triton's ocean is much smaller than in Europa, but still cannot be completely ruled out. The ammonia that is likely present in Triton's marine waters could be instrumental in lowering the freezing point of the water, thus making it more conducive to supporting life. Needless to say, however, these are only suppositions, probably destined to remain so until an automated mission can reach the surface of the big moon. Nicknamed Triton for its 3-pronged goals, the mission would probe the magnetic field to determine the presence of an ocean, map the entirety of the surface, and use a camera to gauge the activity of plumes. In 2021, however, NASA preferred to prioritize missions to Venus, also believing that simply flying over Triton by the Triton probe would not bring significant scientific results. Currently under approval is the Neptune Odyssey. Proposal targets a launch in 2033 using the Space Launch System and a 16-year cruise directly to Neptune, with launch windows yearly during the 2030s. The cruise could be shortened to 12 years with gravity-assisted Jupiter, but this would require a launch before 2032. A 220-kilogram atmospheric probe will be released from the orbiter before orbital insertion at Neptune and descend 37 minutes into Neptune's atmosphere to study its composition, dynamics, and processes.
After achieving Neptune orbit, the orbiter will conduct at least 46 flybys of Triton over the 4-year main science phase, achieving near global coverage of the moon while simultaneously studying Neptune and other moons. The orbiter would then orbit progressively closer to Neptune and its rings on a grand finale, similar to the grand finale of Cassini, and eventually be destroyed in Neptune's atmosphere for planetary protection purposes. But these are all things that will happen perhaps 20 years from now, and a future that seems beyond our reach at the moment. For now, all we can do is travel with our imagination and lose ourselves among those mysterious and immensely remote places.